This video is sponsored by Skillshare.
This is a rank 1 matrix, because every row is simply a constant multiple of the first. Second row is twice the first, the third row is -4 times the first. You could also say the same thing about the columns, just constant multiples of each other, like the third column is twice the first. But what's nice about rank 1 matrices is they can be written in this form, where you take the first row, put it here, and these are just those constants we're multiplying by. Using matrix multiplication as normal, this multiplies to our 3 by 3 rank 1 matrix. What we just did was, in a simple way, data compression. The 3 by 3 matrix requires 9 numbers to store, but writing in this way only requires 6 numbers to store. It went from 3 times 3 to 3 plus 3. If we had a 10 by 10 rank 1 matrix, we could write it as a 10 by 1 matrix times a 1 by 10. So in this case, we go from 100 numbers to 20. Again, 10 times 10 to 10 plus 10. Now, this matrix is not a rank 1 matrix. However, it is the sum of two different rank 1 matrices. And this is one of the most important concepts in linear algebra. Every matrix can be represented as a sum of rank 1 matrices. This is the idea behind singular value decomposition, or SVD, but I'm going to start with an application of that, which is image compression. Because digital images are really just matrices, where each entry is a number representing the pixel value or color. A 1000 by 1000 pixel image is represented by a 1000 by 1000 matrix, each entry being that pixel value. And as we just saw, any matrix can be represented as a sum of rank 1 matrices, each holding much less data than the original. So to compress an image, the idea is simple. Use only some of the rank 1 matrices, throw out the rest, and hopefully you get something that looks similar to the original image. So let's see an example. Here's a 5 by 5 image of the number 4. We'll say a black pixel is represented by the number 0 and a white pixel by the number 1. Anything in between is just a shade of gray, which is darker if it's closer to 0 and lighter if it's closer to 1. So here's the matrix representing our image. You can easily see the number 4 made up of all 1s. Now this matrix can also be written as the sum of 3 rank 1 matrices. Finding these matrices and understanding why there's 3 of them is what singular value decomposition is about, by the way, but ignore that for now. Now with these 3 rank 1 matrices, what I'm going to do is just throw out this last one and then combine the 2 that remain to get a new matrix. So now if we were to make the associated image with these pixel values, we get this here. And by the way, for any pixel value greater than 1, the pixel color is just white and any negative pixel value is black. A little weird since we fixed our values between 0 and 1, but still, here we have a compressed image where you can still kind of tell the original image was a 4. We lost some data, lost some detail, but we can still make out what the original image was. The original image was a 5 by 5 matrix, meaning we had to store 25 numbers. But this new image, represented as 2 rank 1 matrices, only requires 20 numbers to be stored. This is the idea behind image compression. Now, I could have compressed the image even more and only used the first rank 1 matrix, reducing 25 numbers to just 10, and this is what we get in that case. This is probably too much compression, since it's hard to tell this was originally a 4. But using SVD, we can kind of choose how much detail we want to retain by choosing how many of the rank 1 matrices to throw out. Now, to show a little of the math, I'm not going to derive singular value decomposition, but here's what you should know if you're learning it or soon will be. SVD says any matrix A can be factored into the product of 3 special matrices, U, sigma, and V transpose, where the middle matrix, sigma, is always diagonal, or pseudo-diagonal, which isn't really a word, but basically sigma is always the same size as A. So if A is rectangular, sigma might look like this, where it is diagonal, but with padded zeros. But same idea. Anyways, this doesn't seem to say anything about A being a sum of rank 1 matrices. I mean, this is a product. But it's also a sum because of that middle matrix. And it's easier to see if we just use numbers. So if A is this matrix, then its singular value decomposition is this here. And how you get that is not what this video is about. But because sigma will always be diagonal, this can all be rewritten as the first number in sigma times the first column of that first matrix U times the first row of the last matrix V transpose, plus the second number along the diagonal of sigma times the second column of U times the second row of V transpose. This isn't obvious by just looking, but it's basic matrix multiplication. It's just another way to rewrite this when that middle matrix is diagonal. And look at that. These are just rank 1 matrices, which get added up. They're each multiplied by a constant, but they're they're still rank 1. This is what SVD tells us. On the surface, it just looks like there's always a way to factor a matrix into 3 other matrices. But it really says any matrix can be represented as the sum of rank 1 matrices, each weighted by the numbers along the diagonal of that middle matrix sigma. And what image compression does is it throws away the rank 1 matrices with the smallest weights. So when we threw away that last matrix in our previous example, that wasn't random. It was the one with the smallest weight that I didn't show. The SVD of our original matrix is this here that I just found with Wolfram Alpha. Notice it has 3 non-zero values along the diagonal of sigma. That means the original matrix can be written as the sum of 3 rank 1 matrices, as we saw. The one I threw away was the one multiplied by 0.73, the smallest number. So before, when I wrote these out, I had multiplied the weights in, which is why you didn't see them. But if I write it in more proper form with the weights on the outside, you get this. And then you throw away the smallest weighted rank 1 matrix and use the rest, which is exactly what we did to get our compressed image. And with more complicated images, you can choose how many of the lowest weight rank 1 matrices you want to throw out. So that is the idea behind image compression. And if you want to learn how to program something like this, you can take several kinds of programming courses over at Skillshare, the sponsor of this video. Skillshare is the largest online learning community for creatives, with thousands of classes led by industry experts, from artificial intelligence or JavaScript. They have several classes made for beginners, so anyone can just
Hey everybody. Today we're talking about the gamma distribution. This is a continuous probability distribution that's most frequently used to model waiting time for a certain number, call it alpha, of occurrences of a randomly occurring event, like calls to a pizza place or defects in a production line. Technically, events like that are said to occur according to a Poisson process, and the key thing there is that the events all need to be independent of one another. So let's get some technical stuff here. Let x be the random variable in question, the elapsed time before the alpha event, and let theta be the average time between occurrences. Then the cumulative distribution function for that random variable x is just the probability, 1 minus the probability of getting fewer than alpha occurrences before time x. And when we're talking about probability for a certain number of occurrences in a fixed amount of time, we're talking about a Poisson distribution. That has a probability mass function given by the gobbledygook inside that summation formula. I have a whole video on the Poisson distribution. I'll throw a link up top. If you're not familiar with that, you really should start with that before diving into the gamma distribution.
Hi, I'm Eagle. I'm a data science student in London, and in this video I'm going to explain to you what a gamma distribution is. This distribution is used a lot, particularly when modeling claim severity in insurance, so it's definitely a concept well worth knowing if you're a data scientist. The things we'll cover in this video are what is a gamma distribution, It's no lie that being a data scientist is probably one of the coolest jobs out there at the moment, particularly with the rise of AI last year. In this video, I want to detail my journey into how I became a data scientist and offer advice for how you become one in 2024. It's important to mention that not everyone's journey is the same, but hopefully this video will strike some inspiration or some general guidance on how you can become a data scientist. We'll start with covering my background, how I discovered data science, how I learned data science, how I got my first job, and general advice for you looking to break into the field. So let's get into it. I come from quite a heavy maths background. My mum has a maths degree, both my grandparents studied physics, and my great-granddad was even an engineer. So I was always naturally inclined and pushed into that direction of STEM subjects. I remember when I was 12 years old, is what really got me into physics. I was watching The Big Bang Theory, and they were talking about things such as quantum gravity, general relativity. And these topics were really interesting, so I went and Googled all about them. Obviously, I didn't know much of anything at that point, but they were still very interesting to me, and that's why I decided to pursue physics. For my GCSEs, I got 4 A stars, 3 A's and 5 B's, which was not bad at all. However, it wasn't exactly genius level, and at that time, I thought I was much smarter than I was, and my work ethic was really poor. My 4 A stars were in maths, physics, further maths and chemistry, so those were the 4 subjects I took to A level. At A level, nothing much changed. I was still being quite lazy, wasn't working too hard because in reality, I thought I was smarter than I was. I was quite delusional at the time, and I thought I could get into the best universities, even though, like I said, I wasn't working very hard. So in the UK, you get a choice of 5 universities that you can apply to. So my 5 choices were Oxford, Imperial, Nottingham, Manchester, and Southampton. Now, obviously, both Oxford and Imperial both rejected me as they are the top institutions in the world, and at that point in time, my grades and work ethic, like I said, weren't very good. However, Manchester, Southampton, and Nottingham all gave me offers. I firmed choice Manchester, which required me to get A star, A star, A, and my insurance choice was Southampton, where I needed 3 A's. So results day comes around for my A level results, and let's just say I didn't do too well as I was expecting. I got A star in maths, a B in further maths, but a C in physics. So for someone who wants to study physics at university, that's not great, and Manchester and Southampton both rejected me. In the UK, we have something called clearing. Now, clearing is where, on results day, universities may have some space on certain courses, and people who didn't get into their firm or insurance choice can apply to those universities. And luckily, the University of Surrey offered me a place to study physics with astronomy come September 2017. At Surrey is where I really learned that there is no substitute for hard work. I know it's a cliche, but it's true. In my first 2 years, I had a much better work ethic than I did in my school days, and in my first year I got a first, and in my second year I also got a first. At the end of my second year, I got accepted onto the master's program. As part of the master's program, you have to do a year of research. It's kind of like a mini PhD, and my year was done at the National Physical Laboratory in Teddington, or NPL for short. And my thesis was on measuring air temperature gradients using acoustic thermometry. During this year, I enjoyed it. However, physics research from that small snippet I had wasn't quite what I envisioned it being like. And in reality, I found things to move a lot slower than I would have liked, and that wasn't quite for me, and I kind of fell out of love of physics. I still remember to this day exactly how I discovered data science. After coming back from a day of work at MPL, a video appeared on my YouTube homepage, and it was DeepMind's AlphaGo documentary on where they trained an AI bot to beat the Go World Champion Lee Sedol. After watching the documentary, I became fascinated about how they trained this AI, like what algorithms did they use and what kind of process did they take. I was looking into reinforcement learning, deep learning, Markov chains, all these things. Obviously, at that point in time, I didn't understand everything, but I found it also interesting. So I looked online of basically opportunities and what kind of people or what kind of professions use machine learning, and that's how I stumbled across data science. Like most people, I had the age-old question, how do I learn data science? Data science cuts and intersects into so many fields, maths, statistics, to pure science, that it seems overwhelming. However, if you break down your learning to small chunks, it's very doable. Coming from a physics background, I pretty much had all the prerequisite knowledge I needed. I knew the algebra, I knew calculus, and I knew statistics. So that means I could jump straight into the machine learning and understanding how the algorithms work. The first course I took was Andrew Nook's course called the Machine Learning Specialization. I took this course back in 2020, and this when it was still the 2012 version, and all the exercises were adopted on MATLAB. It's been revamped, and it's got more cutting-edge algorithms in there, such as reinforcement learning, written systems, and it's also taught in Python. At this point in time, I only had experience in one programming language, and that was Fortran. So we got taught Fortran in my first 2 years of university, and for those of you who don't know what Fortran is, it's probably one of the oldest high-level programming languages out there. It was written in the 1950s. With it being my first programming language, it made me not really like coding that much because everything was manual, hard, there's not many packages available for Fortran. Reflecting on it, learning Fortran was kind of a blessing in disguise because it really got me to rethink programmatically, and like I said, everything has to be done from scratch. And so when I went about learning Python, it was so much easier for me. The way I learned Python was by simply contacting one of the lecturers at my university who taught a computational physics course. Basically, I asked him for the course notes, and it was just an introduction to Python. In reality, any intro to Python course would have been sufficient. I also took the tutorial sprint Python course, and it basically taught me all the things that was in those lecture notes. The main things I learned were Python syntax, functions, loops, classes, all kind of the regular things you need to know behind a programming language. Most jobs nowadays when you're a data scientist. After upskilling in machine learning, Python and SQL, I then basically started building some really simple projects. What I did is I would get some data from Kaggle, and I'll just randomly apply just loads of machine learning models to these data sets. I will link in the description below a lot of these projects, but comparing them to my abilities now, they weren't very good, but they allowed me to get my hands dirty and just try out loads of models. I built linear regression, logistic regression, decision trees, just a range of algorithms, and it really taught me how they work and how to apply them to a real life problem. The hardest part by far is securing the first job. You dedicate a lot of time to learning all these skills with the hope that you'll land that first role. I'm not joking when I said I applied to over 300 roles in my final year of university trying to get this first data science job. So when it comes to your first role, I honestly believe it's purely a numbers game. You really just have to put yourself out there, have practice in interviews, have practice in these take-home assessments to land that first role. I got my first role at an insurance company, kind of mid-level size in the UK. It wasn't some fancy FANG or quad hedge fund. Like I said, it was a regular firm that was really good, and I worked with some amazing people. You don't need to work at one of these top companies, particularly at the start, because in reality, in some of these smaller companies, you may learn more because you may be asked to do more things, be more hands-on with a lot of infrastructure. Like anything in life, it's really up to you to excel and put in effort. You can not grow at all in big companies, and you can grow a lot in small companies. The final thing I want to discuss is how you can stand out as a data scientist. In my opinion, these three things are very simple to do, and they give you so much more reward than the effort you put into them. The first one is make sure you have a GitHub profile and populate it. On the screen is what mine looks like. Again, mine's not that fancy, but it does have some, it looks good and it has some nice things added to it. What languages I know, what I do, and some basic repos on my past projects. You can do the same easily. In fact, just copy my template and add some basic repos of you basically learning Python. It doesn't need to be too complicated, but I promise you, most people applying for entry-level jobs won't even have this. The second one is write a blog post. I'm still amazed at why people think this is so much harder than it really is. The goal of writing a blog post, particularly if you're just trying to land a job, you're not trying to make the post go viral. It's more just to showcase your learning and show that you're interested and you're curious and willing to document your work. The simplest way you can write a blog post is, for example, say you learn how to implement functions in Python. Write a blog post about how you implement functions in Python. It really is that simple. Don't overcomplicate it. The final one, which is a bit more tricky, and that is enter a Kaggle competition and do reasonably well. Now, what Kaggle will show to the employer is that you're able to break down a business problem into code in a data science way. And that's really useful because your job as a data scientist is to unify business with data and to solve that problem. The thing I want to stress is that there's no one best way to become a data scientist, but my journey hopefully gives you some inspiration or some guidance or even some tips on how you can tailor your learning or the steps you can take to become one in 2024. I highly recommend you action on those three key things I mentioned at the end of the video. That is, get a GitHub profile, write a simple blog post, and maybe enter a Kaggle competition. I have been working as a data scientist now for about 3 years, and in this video, I want to shed some light and explain the brutal truth behind what is insight into where things can be improved. And data scientist now for about 3 years. And in this video, I want to shed some light and explain the brutal truth behind what it's actually like being a data scientist. Let's get into it. So what actually is a data scientist? And make processes a lot more efficient than they would if they were just operated by humans. Common problems that data scientists may work on is predicting if a credit card payment was fraudulent or not, recommending the right products to certain customers on e-commerce websites, and also generating the right kind of insurance policy for a customer. Data science is such a big area. So what we find is that as data scientists get later on in their career, they will often specialize in one particular area, like recommendation systems, reinforcement learning, and forecasting. And they will also probably specialize in one particular industry domain. So the work I do as a data scientist is that I work in a cross-functional team, and my team mainly focuses on optimization and forecasting type problems. Much of my day-to-day work revolves around trying to improve the models and also providing some idea of the model analysis, pipeline, best way of deploying an algorithm. From my general experience, this one is the idea of having embedded data scientists. This is kind of how I work in my cross-functional team after one area, in-house consultancy, set on tasks, so you work on a range of problems. So both of these kind of systems have their I find that people often really glamorize working in tech online. Like, it seems to be all coffee, chat, coding an hour a day, and yet somehow you make 6 figures. In reality, this is not the case, but the workday is still very interesting compared to a lot of other professions. My general experience is that the workday typically starts at 9 o'clock, where you have a morning stand-up, and then 9:30 till 10:30, you have some sort of sync or meeting with product managers, stakeholders, data scientists, just some meeting to discuss recent developments. Then between 10:30 and 12 to 12:30, you'll have a work block where you do some coding. Then 12:30 to 1:30, you'll typically have your lunch break, and then after that, you have another coding block from 1:30 to about 4, and then 4 to 5, you may have another meeting or sync with stakeholders. Then from 5 to 5:30, you basically wrap off the day, answer emails, Slack messages, and kind of get organized for tomorrow. It's important to mention that we don't only just code as data scientists. We're kind of like a linchpin between the business and tech side. So some days I may be doing presentations for stakeholders and explaining what my data and my models are really doing to the business. The reason I'm a data scientist can be boiled down into 4 main reasons. The first one is that the work is just so interesting. I mean, we're currently in this big AI revolution. So as a data scientist, I'm pretty much right at the forefront of all the latest developments in machine learning, AI, deep learning, whatever you name it, all these buzzwords. And it's just really interesting because data science, like I said earlier, is such a big field. So you can always bet there's something new to learn, and you can never learn everything. And that idea of constantly developing, learning new interesting things to improve your career is something that I really love. The second one is that the flexibility and the work-life balance. Tech jobs are generally quite well known to have better work-life balance than other careers like banking or law. Most kind of jobs I've seen for data science work no longer than 8 to 6. But most of them are normally around 9 to 5:30. And with that, a lot of tech-based jobs normally have quite a hybrid working policy, so you can expect to work kind of a few days or a couple of days from home in the week. I personally love this because all that time I would have wasted commuting or working till 10 o'clock if I was a lawyer banker, I can spend pursuing my other passions, such as creating YouTube videos, writing blogs, playing hockey. Just gives me a lot more variability and kind of freedom to pursue other ventures that I'm also interested in, as well as data science. The third one is that the compensation in data science is pretty good. I mean, it's pretty well known that tech generally pays quite well, particularly in North America, where it's not unheard of for data scientists to be earning 200k plus. In the UK and the EU, it's slightly less, but it's still above average compared to the general median salary of the region. And the final one is that as a data scientist, you can work in so many different industries. I've only worked for 3 years, and I've only worked in both insurance and e-commerce. So if there's an industry that you're really passionate about, then chances are, as a data scientist, you can probably get into it fairly easily. So the final point is that should you be a data scientist? Well, of course you should, but only if you want to. Data science is a great career, like I've just said, but it's not easy all the time. And if you don't like coding, maths, statistics, and constantly learning things, then it may not be the right fit for you. I have a whole separate video explaining exactly the things that you should be comfortable with if you want to become a data scientist. You can find a link on screen here. If you enjoyed this video, make sure you click the like and subscribe button, and I'll see you in the next one. I have been a data scientist now for over 3.5 years, and in this video, I want to go over all learning data science, with all the resources and sufficient material that will really enhance your journey. I somewhat had a plan when I was first beginning, but I wish it was more concrete and more strategic, because I kind of had the right idea, but if I kind of had all my baskets in line, whatever you want to call it, then I'm sure I would have learned all the information a lot quicker than I did. The general order you should learn things is first you want to learn the maths, and the three main areas are linear algebra, calculus, probability statistics. After you've learned the fundamental maths, it's then to learn the coding. Python and SQL are the main language you need to know for data science. After coding, it's then time to learn some machine learning theory. This is all the basics around linear regression, logistic regression, SVMs, decision trees, neural networks. That. And finally, after you've learned all these topics, it's now time to do some projects to really solidify your understanding. I have whole videos on these topics, which I'll link in the description below for you to check out. People always ask me something like, should I take this course to really bolster my application? I mean, taking a course will definitely not negatively impact your application, but you're much better off just building something instead. I see. Now, there's no point in learning all these things, doing loads of projects, if you don't adequately show them on your CV or portfolio. A well-polished and concise CV goes a long way in getting you through the door. I have a whole video explaining exactly what should be on your data science resume, which I'll link in the description below. In a similar vein, a CV or resume is only just one page describing your work and activities, but I'm sure there's so much more that you could say. That's why I also recommend having some sort of personal website or portfolio where you have more detail about yourself. Think of your CV as a business card to your personal portfolio, which contains the whole business, aka you. I plan on making a whole video explaining exactly how I build my personal website, but in a nutshell, I use Hugo to have great templates, and I deploy it on Cloudflare. You can simply just Google how to create a data science portfolio, and there'll be so many examples and tutorials. It doesn't need to be too complicated, just start something simple as an initial step, and then over time you can upgrade, make it more complex or fancy, whatever you want. The point is just have one at the beginning, and that will be pretty much 80% of the way there. This one is key for me, because you're obviously learning data science to get a job in the field. However, you don't know what you don't know. So whilst learning data science, building projects, doing all these things, I'll actively be looking to apply for jobs as well. Now, the reason you want to apply for jobs whilst learning data science is so that you can get more active feedback from where you're missing knowledge. For example, let's say you go to an interview as a coding interview, and let's say they ask a question about dictionaries and Python. You may have no clue how dictionaries work, but that something you probably didn't know before. So that interview is going to be direct feedback on areas you can learn and improve upon. This happened to me a lot of time, and it's partly the reason why I applied for 300 jobs. But those 300 jobs allow me to create micro refinements and really upgrade my knowledge, because I knew the area which I was weak on. And I only got that through these interviews and technical online tests. If I didn't do that, then I'll probably miss some gaps, and I'll spend a lot of time just learning things without actually learning the right stuff. So if you keep your network in the short term, it will allow you to understand how other people are approaching learning, the resources and courses they're using that may benefit you. It's also nice to know that there's other people in the same boat, and you can discuss different strategies. Derive first principles, and a basic example in Python. So let's get into it. So let's start quickly recapping over where the gamma distribution really comes from. So It comes from something called the exponential distribution, which is something I did my previous video on, so feel free to check that out if you want more information. But the exponential distribution infers the probability of the waiting time between events in the Poisson process. The Poisson process is something where we expect a number of rates to happen in a certain time period. Again, I did a video on the Poisson distributions, so I won't spend too much time over in this video. So if you want to learn more about that, make sure to check it out. I've linked them on the screen here, so you can visit them both. Now, the gamma distribution is basically an extension of the exponential distribution, and what it's saying is that, the exponential distribution only infers the probability of until the first event happens, but a gamma distribution infers the probability until the nth event happens. So you can see it's kind of like a generalization and extending what we're trying to calculate here into n times instead of just one time. So we can derive the gamma distribution by saying we want to wait a certain time t, big T, for the nth event to happen. For the gamma distribution, in this case, t is a random variable that we want to calculate. This means we need n-1 events to happen in some sort of other time t. So mathematically, all we have is this. What we're saying is we want the probability of, essentially of t being greater than t. So we're saying, again, it's hard to differentiate between big and small t in this case. But what we're saying is that we want to look at the probability of 0 events, or 1 event, or 2 events, or 3 events happening in time n-1 events in time t. And we can take that away because then we know
statistics is super important if you are planning to build a career in data science. In today's video, we are going to talk about 3 books
This is a Galton board. Maybe you've seen one before. It's a popular demonstration of how even when a single event is chaotic and random, with an effectively unknowable outcome, it's still possible to make precise statements about a large number of events. namely how the relative proportions for many different outcomes are distributed. More specifically, the Galton board illustrates one of the most prominent distributions in all of probability, known as the normal distribution, more colloquially known as a bell curve, and also called a Gaussian distribution. There's a very specific function to describe this distribution. It's very pretty, we'll get into it later. But right now, I just want to emphasize how the normal distribution is, as the name suggests, very common. It shows up in a lot of seemingly unrelated contexts. If you were to take a large number of people who sit in a similar demographic and plot their heights, those heights tend to follow a normal distribution. If you look at a large swath of very big natural numbers, and you ask how many distinct prime factors does each one of those numbers have, the answers will very closely track with a certain normal distribution. Now, our topic for today is one of the crown jewels in all of probability theory. It's one of the key facts that explains why this distribution is as common as it is, known as the central limit theorem. This lesson is meant to go back to the basics, giving you the fundamentals on what the central limit theorem is saying, what normal distributions are, and I want to assume minimal background. We're going to go decently deep into it, but after this, I'd still like to go deeper and explain why the theorem is true, why the function underlying the normal distribution has the very specific form that it does, why that formula has a pi in it, and, most fun, why those last two facts are actually more related than a lot of traditional explanations would suggest. That second lesson is also meant to be the follow-on to the convolutions video that I promised, so there's a lot of interrelated topics here. But right now, back to the fundamentals, I'd like to kick things off with an overly simplified model of the Galton board. In this model, we will assume that each ball falls directly onto a certain central peg, and that it has a 50-50 probability of bouncing to the left or to the right. And we'll think of each of those outcomes as either adding one or subtracting one from its position. Once one of those is chosen, we make the highly unrealistic assumption that it happens to land dead on in the middle of the peg adjacent below it, where again, it'll be faced with the same 50-50 choice of bouncing to the left or to the right. For the one I'm showing on screen, there are 5 different rows of pegs, so our little hopping ball makes 5 different random choices between +1 and -1, and we can think of its final position as basically being the sum of all of those different numbers, which in this case happened to be 1, and we might label all of the different buckets with the sum that they represent. As we repeat this, we're looking at different possible sums for those 5 random numbers. And for those of you who are inclined to complain that this is a highly unrealistic model for the true Galton board, let me emphasize the goal right now is not to accurately model physics. The goal is to give a simple example to illustrate the central limit theorem. And for that, idealized though this might be, it actually gives us a really good example. If we let many different balls fall, making yet another unrealistic assumption that they don't influence each other, as if they're all ghosts, then the number of balls that fall into each different bucket gives us some loose sense for how likely each one of those buckets is. In this example, the numbers are simple enough that it's not too hard to explicitly calculate what the probability is for falling into each bucket. If you do want to think that through, you'll find it very reminiscent of Pascal's triangle. But the neat thing about our theorem is how far it goes beyond the simple examples. So to start off at least, rather than making explicit calculations, let's just simulate things by running a large number of samples and letting the total number of results in each different outcome give us some sense for what that distribution looks like. As I said, the one on screen has 5 rows, so each sum that we're considering includes only 5 numbers. And the basic idea of the central limit theorem is that if you increase the size of that sum, for example, here that would mean increasing the number of rows of pegs for each ball to bounce off, then the distribution that describes where that sum is going to fall looks more and more like a bell curve. Here, it's actually worth taking a moment to write down that general idea. The setup is that we have a random variable, and that's basically shorthand for a random process where each outcome of that process is associated with some number. We'll call that random number x. For example, each bounce off the peg is a random process modeled with 2 outcomes. Those outcomes are associated with the numbers -1 and +1. Another example of a random variable would be rolling a die, where you have 6 different outcomes, each one associated with a number. What we're doing is taking multiple different samples of that variable and adding them all together. On our Galton board, that looks like letting the ball bounce off multiple different pegs on its way down to the bottom. And in the case of a die, you might imagine rolling many different dice and adding up the results. The claim of the central limit theorem is that as you let the size of that sum get bigger and bigger, then the distribution of that sum, how likely it is to fall into different possible values, will look more and more like a bell curve. That's it. That is the general idea. Over the course of this lesson, our job is to make that statement more quantitative. We're going to put some numbers to it, put some formulas to it, show how you can use it to make predictions. For example, here's the kind of question I want you to be able to answer by the end of this video. Suppose you rolled the die 100 times and you added together the results. Could you find a range of values such that you're 95% sure that the sum will fall within that range? Or maybe I should say find the smallest possible range of values such that this is true. The neat thing is, you'll be able to answer this question whether it's a fair die or if it's a weighted die. Now let me say at the top that this theorem has 3 different assumptions that go into it, 3 things that have to be true before the theorem follows. And I'm actually not going to tell you what they are until the very end of the video. Instead, I want you to keep your eye out and see if you can notice and maybe predict what those 3 assumptions are going to be. As a next step, to better illustrate just how general this theorem is, I want to run a couple more simulations for you focused on the dice example. Usually, if you think of rolling a die, you think of the 6 outcomes as being equally probable. But the theorem actually doesn't care about that. We could start with a weighted die, something with a non-trivial distribution across the outcomes, and the core idea still holds. For the simulation, what I'll do is take some distribution, like this one that is skewed towards lower values. I'm going to take 10 distinct samples from that distribution, and then I'll record the sum of that sample on the plot on the bottom. Then I'm going to do this many, many different times, always with a sum of size 10, but keep track of where those sums ended up to give us a sense of the distribution. And in fact, let me rescale the y direction to give us room to run an even larger number of samples. And I'll let it go all the way up to a couple thousand, and as it does, you'll notice that the shape that starts to emerge looks like a bell curve. Maybe if you squint your eyes, you can see it skews a tiny bit to the left, but it's neat that something so symmetric emerged from a starting point that was so asymmetric. To better illustrate what the central limit theorem is all about, let me run 4 of these simulations in parallel, where on the upper left, I'm doing it where we're only adding 2 dice at a time. On the upper right, we're doing it where we're adding 5 dice at a time. The lower left is the one that we just saw, adding 10 dice at a time. And then we'll do another one with a bigger sum, 15 at a time. Notice how on the upper left, when we're just adding 2 dice, the resulting distribution doesn't really look like a bell curve. It looks a lot more reminiscent of the one we started with, skewed towards the left. But as we allow for more and more dice in each sum, the resulting shape that comes up in these distributions looks more and more symmetric. It has the lump in the middle and fade towards the tail's shape of a bell curve. And let me emphasize again, you can start with any different distribution. Here I'll run it again, but where most of the probability is tied up in the numbers 1 and 6, with very low probability for the mid values. Despite completely changing the distribution for an individual roll of the die, it's still the case that a bell curve shape will emerge as we consider the different sums. Illustrating things with a simulation like this is very fun, and it's kind of neat to see order emerge from chaos, but it also feels a little imprecise. Like in this case, when I cut off the simulation at 3,000 samples, even though it kind of looks like a bell curve, the different buckets seem pretty spiky, and you might wonder, is it supposed to look that way, or is that just an artifact of the randomness in the simulation? And if it is, how many samples do we need before we can be sure that what we're looking at is representative of the true distribution? Instead, moving forward, let's get a little more theoretical and show the precise shape that these distributions will take on in the long run. The easiest case to make this calculation is if we have a uniform distribution, where each possible face of the die has an equal probability, 1/6. For example, if you then want to know how likely different sums are for a pair of dice, it's essentially a counting game, where you count up how many distinct pairs take on the same sum, which in the diagram I've drawn, you can conveniently think about by going through all of the different diagonals. Since each such pair has an equal chance of showing up, 1 in 36, all you have to do is count the sizes of these buckets. That gives us a definitive shape for the distribution describing a sum of 2 dice, and if we were to play the same game with all possible triplets, the resulting distribution would look like this. Now what's more challenging, but a lot more interesting, is to ask what happens if we have a non-uniform distribution for that single die. We actually talked all about this in the last video. You do essentially the same thing. You go through all the distinct pairs of dice which add up to the same value. It's just that instead of counting those pairs, for each pair you multiply the 2 probabilities of each particular face coming up, and then you add all those together. The computation that does this for all possible sums has a fancy name, it's called a convolution, but it's essentially just the weighted version of the counting game that anyone who's played with a pair of dice already finds familiar. For our purposes in this lesson, I'll have the computer calculate all that, simply display the results for you, and invite you to observe certain patterns, but under the hood, this is what's going on. So, just to be crystal clear on what's being represented here, if you imagine sampling two different values from that top distribution, the one describing a single die, and adding them together, then the second distribution I'm drawing represents how likely you are to see various different sums. Likewise, if you imagine sampling three distinct values from that top distribution and adding them together, the next plot represents the probabilities for various different sums in that case. So, if I compute what the distributions for these sums look like for larger and larger sums, well, you know what I'm going to say, it looks more and more like a bell curve. But before we get to that, I want you to make a couple more simple observations. For example, these distributions seem to be wandering to the right, and also they seem to be getting more spread out and a little bit more flat. You cannot describe the central limit theorem quantitatively without taking into account both of those effects, which in turn requires describing the mean and the standard deviation. Maybe you're already familiar with those, but I want to make minimal assumptions here, and it never hurts to review, so let's quickly go over both of those. The mean of a distribution, often denoted with the Greek letter mu, is a way of capturing the center of mass for that distribution. It's calculated as the expected value of a random variable, which is a way of saying you go through all of the different possible outcomes, and you multiply the probability of that outcome times the value of the variable. If higher values are more probable, that weighted sum is going to be bigger. If lower values are more probable, that weighted sum is going to be smaller. A little more interesting is if you want to measure how spread out this distribution is, because there's multiple different ways you might do it. One of them is called the variance. The idea there is to look at the difference between each possible value and the mean, square that difference, and ask for its expected value. The idea is that whether your value is below or above the mean, when you square that difference, you get a positive number, and the larger the difference, the bigger that number. Squaring it like this turns out to make the math much nicer than if we did something like an absolute value, but the downside is that it's hard to think about this as a distance in our diagram because the units are off. Kind of like the units here are square units, whereas a distance in our diagram would be a kind of linear unit. So another way to measure spread is what's called the standard deviation, which is the square root of this value. That can be interpreted much more reasonably as a distance on our diagram, and it's commonly denoted with the Greek letter sigma. So, M for mean, S for standard deviation, but both in Greek. Looking back at our sequence of distributions, let's talk about the mean and standard deviation. If we call the mean of the initial distribution mu, which for the one illustrated happens to be 2.24, hopefully it won't be too surprising if I tell you that the mean of the next one is 2 times mu. That is, you roll a pair of dice, you want to know the expected value of the sum, it's 2 times the expected value. Value for a single die. Similarly, the expected value for a sum of size 3 is 3 times mu, and so on and so forth. The mean just marches steadily on to the right, which is why our distributions seem to be drifting off in that direction. A little more challenging, but very important, is to describe how the standard deviation changes. The key fact here is that if you have two different random variables, then the variance for the sum of those variables is the same as just adding together the original two variances. This is one of those facts that you can just compute when you unpack all the definitions. There are a couple nice intuitions for why it's true. My tentative plan is to just actually make a series about probability and talk about things like intuitions underlying variance and its cousins there. But right now, the main thing I want you to highlight is how it's the variance that adds, it's not the standard deviation that adds. So critically, if you were to take n different realizations of the same random variable and ask what the sum looks like, the variance of that sum is n times
Let's do DSA. Blind 70 Pro. How do you reverse a linked list? So we have a head. What is the solution? So we have a two-pointer method. So priv fucking up. The fuck? P. No, nigga. Bro. What the hell? Current will be hello. Hello. மைக் மியூட் பண்ணி வச்சிருக்கா. கேக்குது. இல்லை இப்போதான் மெசேஜை பார்த்தேன். அங்கே 9:20. அதாவது மெசேஜ் அனுப்புனேன். அதெல்லாம் மெசேஜ் அனுப்பிச்சுடா. போயிட்டு பாரு. என்ன போயிட்டு பாடுறா, நான் அமிச்சதுனடா. சரி எடு நீ. ஏய் போயிட்டு பாடுறா. வளர் கொஞ்சம் பாரு. சரி லீட் கோட் நீ என்ன பண்றியா இல்லையா, பாத்தியா இல்லையா அதான்? ஆ டேய் லீட் கோட் பாத்தியா இல்லையா அந்த வீடியோ? சரி ஓகே. சரி ஓகே. சரி நான் லீட் கோட் படிக்கணும் தான் நான் இருக்கேன். நான் லீட் கோட் படிக்கணும்னா வா, இல்லைனா சேல்ஸ் ஃபோர்ஸ் எனக்கு ஐடியா இல்லை எனக்கு. சரிடா ஓகே. உனக்கு இன்டர்வியூ அதில் வருமா? அதெல்லாம் சேல்ஸ் ஃபோர்ஸில் இன்டர்வியூ வருமா? இல்லை கோடிங் இன்டர்வியூ வருமான்னு கேட்டேன்டா. அதுக்கு ஓகே. சரி ஓகே. சரி ஓகேடா. சரி நீ வேணும்னா ஐ மீன் லீட் கோட் வேணும்னா வா. நான் ஒரு 2-3 மாதம் லீட் கோட் நான் பண்ண போகிறேன் சைடில். டேட்டா மெயினாக ஏதாவது சாஃப்ட்வேர் இன்ஜினியரிங் ஜாப் லண்டனில், இல்லைனா ஏதாவது டேட்டா சயின்ஸ் ரிலேட்டடாக. சரி ஓகேடா. சரிடா பார்ப்போம். வேறு ஓகே.
even though our distributions are getting spread out, they're not spreading out all that quickly. They only and talk about things like intuition's underlying variance and its cousins there. But right now, the main thing I want you to highlight is how it's the variance that adds, it's not the standard deviation that adds. So critically, if you were to take n different realizations of the same random variable and ask what the sum looks like, the variance of that sum is n times the variance of your original variable, meaning the standard deviation, the square root of all this, is the square root of n times the original standard deviation. For example, back in our sequence of distributions, if we label the standard deviation of our initial one with sigma, then the next standard deviation is going to be the square root of 2 times sigma. And after that, it looks like the square root of 3 times sigma, and so on and so forth. This, like I said, is very important. It means that even though our distributions are getting spread out, they're not spreading out all that quickly. They only do so in proportion to the square root of the size of the sum. As we prepare to make a more quantitative description of the central limit theorem, the core intuition I want you to keep in your head is that we'll basically realign all of these distributions so that their means line up together, and then rescale them so that all of the standard deviations are just going to be equal to 1. And when we do that, the shape that results gets closer and closer to a certain universal shape, described with an elegant little function that we'll unpack in just a moment. And let me say one more time, the real magic here is how we could have started with any distribution, describing a single roll of the die, and if we play the same game, considering what the distributions for the many different sums look like, and we realign them so that the means line up, and we rescale them so that the standard deviations are all 1, we still approach that same universal shape, which is kind of mind-boggling. And now, my friends, is probably as good a time as any to finally get into the formula for a normal distribution. And the way I'd like to do this is to basically peel back all the layers and build it up one piece at a time. The function e to the x, or anything to the x, describes exponential growth. And if you make that exponent negative, which flips around the graph horizontally, you might think of it as describing exponential decay. To make this decay in both directions, you could do something to make sure the exponent is always negative and growing, like taking the negative absolute value. That would give us this kind of awkward sharp point in the middle. But if instead you make that exponent the negative square of x, you get a smoother version of the same thing, which decays in both directions. This gives us the basic bell curve shape. Now if you throw a constant in front of that x, and you scale that constant up and down, it lets you stretch and squish the graph horizontally, allowing you to describe narrow and wider bell curves. And a quick thing I'd like to point out here is that based on the rules of exponentiation, as we tweak around that constant c, you could also think about it as simply changing the base of the exponentiation. And in that sense, the number e is not really all that special for our formula. We could replace it with any other positive constant, and you'll get the same family of curves as we tweak that constant. Make it a 2, same family of curves. Make it a 3, same family of curves. The reason we use e is that it gives that constant a very readable meaning. Or rather, if we reconfigure things a little bit so that the exponent looks like negative 1/2 times x divided by a certain constant which we'll suggestively call sigma squared, then once we turn this into a probability distribution, that constant sigma will be the standard deviation of that distribution. And that's very nice. That readable meaning. Or rather, if we reconfigure things a little bit so that the exponent looks like negative 1/2 times x divided by a certain constant which we'll suggestively call sigma squared, then once we turn this into a probability distribution, that constant sigma will be the standard deviation of that distribution. And that's very nice. But before we can interpret this as a probability distribution, we need the area under the curve to be 1. And the reason for that is how the curve is interpreted. Unlike discrete distributions, when it comes to something continuous, you don't ask about the probability of a particular point. Instead, you ask for the probability that a value falls between two different values. And what the curve is telling you is that that probability equals the area under the curve between those two values. There's a whole other video about this. They're called probability density functions. The main point right now is that the area under the entire curve represents the probability that something happens, that some number comes up. That should be 1, which is why we want the area under this to be 1. As it stands with the basic bell curve shape of e to the negative x squared, the area is not 1, it's actually the square root of pi. I know, right? What is pi doing here? What does this have to do with circles? Like I said at the start, I'd love to talk all about that in the next video. But if you can spare your excitement, for our purposes right now, all it means is that we should divide this function by the square root of pi, and it gives us the area we want. Throwing back in the constants we had earlier, the 1/2 and the sigma, the effect there is to stretch out the graph by a factor of sigma times the square root of 2. So we also need to divide out by that in order to make sure it has an area of 1. And combining those fractions, the factor out front looks like 1 divided by sigma times the square root of 2 pi. This, finally, is a valid probability distribution. As we tweak that value sigma, resulting in narrower and wider curves, that constant in the front always guarantees that the area equals 1. The special case where sigma equals 1 has a specific name. We call it the standard normal distribution, which plays an especially important role for you and me in this lesson. And all possible normal distributions are not only parameterized with this value sigma, but we also subtract off another constant mu from the variable x. And this essentially just lets you slide the graph left and right so that you can prescribe the mean of this distribution. So in short, we have two parameters, one describing the mean, one describing the standard deviation, and they're all tied together in this big formula involving an e and a pi. Now that all of that is on the table, let's look back again at the idea of starting with some random variable and asking what the distributions for sums of that variable look like. As we've already gone over, when you increase the size of that sum, the resulting distribution will shift according to a growing mean, and it slowly spreads out according to a growing standard deviation. And putting some actual formulas to it, if we know the mean of our underlying random variable, and we call it mu, and we also know its standard deviation, and we call it sigma, then the mean for the sum on the bottom will be mu times the size of the sum, and the standard deviation will be sigma times the square root of that size. So now, if we want to claim that this looks more and more like a bell curve, and a bell curve is only described by two different parameters, the mean and the standard deviation, you know what to do. You could plug those two values into the formula, and it gives you a highly explicit, albeit kind of complicated, formula for a curve that should closely fit our distribution. But there's another way for a curve that should closely fit our distribution. But there's another way we can describe it that's a little more elegant and lends itself to a very fun visual that we can build up to. Instead of focusing on the sum of all of these random variables, let's modify this expression a little bit, where what we'll do is we'll look at the mean that we expect that sum to take, and we subtract it off so that our new expression has a mean of 0. And then we're going to look at the standard deviation we expect of our sum and divide out by that, which basically just rescales the units so that the standard deviation of our expression will equal 1. This might seem like a more complicated expression, but it actually has a highly readable meaning. It's essentially saying, how many standard deviations away from the mean is this sum? For example, this bar here corresponds to a certain value that you might find when you roll 10 dice and you add them all up. And its position, a little above -1, is telling you that that value is a little bit less than one standard deviation lower than the mean. Also, by the way, in anticipation for the animation I'm trying to build to here, the way I'm representing things on that lower plot is that the area of each one of these bars is telling us the probability of the corresponding value, rather than the height. You might think of the y-axis as representing not probability, but a kind of probability density. The reason for this is to set the stage so that it aligns with the way we interpret continuous distributions, where the probability of falling between a range of values is equal to an area under a curve between those values. In particular, the area of all the bars together is going to be 1. Now, with all of that in place, let's have a little fun. Let me start by rolling things back so that the distribution on the bottom represents a relatively small sum, like adding together only 3 such random variables. Notice what happens as I change the distribution we start with. As it changes, the distribution on the bottom completely changes its shape. It's very dependent on what we started with. If we let the size of our sum get a little bit bigger, say going up to 10, and as I change the distribution for x, it largely stays looking like a bell curve, but I can find some distributions that get it to change shape. For example, the really lopsided one where almost all the probability is in the numbers 1 or 6 results in this kind of spiky bell curve. And if you'll recall, earlier on, I actually showed this in the form of a simulation. So if you were wondering whether that spikiness was an artifact of the randomness or reflected the true distribution, turns out it reflects the true distribution. In this case, 10 is not a large enough sum for the central limit theorem to kick in. But if instead I let that sum grow and I consider adding 50 different values, which is actually not that big, then no matter how I change the distribution for our underlying random variable, it has essentially no effect on the shape of the plot on the bottom. No matter where we start, all of the information and nuance for the distribution of x gets washed away, and we tend towards this single universal shape described by a very elegant function for the standard normal distribution, 1 over square root of 2 pi times e to the negative x squared over 2. This right here is what the central limit theorem is all about. Almost nothing you can do to this initial distribution changes the shape we tend towards. Now, the more theoretically minded among you might still be wondering, what is the actual theorem? Like, what's the mathematical statement that could be proved or disproved that we're claiming here? If you want a nice formal statement, here's how it might go. Consider this value, where we're summing up n different instantiations of our random variable, but tweaked and tuned so that its mean and standard deviation are 1. Again, meaning you can read it as asking how many standard deviations away from the mean is the sum. Then the actual rigorous no jokes this time statement of the central limit theorem is that if you consider the probability that this value falls between 2 given real numbers, a and b, and you consider the limit of that probability as the size of your sum goes to infinity, then that limit is equal to a certain integral, which basically describes the area under a standard normal distribution between those two values. Again, there are 3 underlying assumptions that I have yet to tell you, but other than those, in all of its gory detail, this right here is the central limit theorem. All of that is a bit theoretical, so it might be helpful to bring things back down to earth and turn back to the concrete example that I mentioned at the start, where you imagine rolling a die 100 times, and let's assume it's a fair die for this example, and you add together the results. The challenge for you is to find a range of values such that you're 95% sure that the sum will fall within this range. For questions like this, there's a handy rule of thumb about normal distributions, which is that about 68% of your values are going to fall within 1 standard deviation of the mean, 95% of your values, the thing we care about, fall within 2 standard deviations of the mean, and a whopping 99.7% of your values will be 100 times mu, which is 350, and its standard deviation will be the square root of 100 times sigma, so 10 times sigma, 17.1. Remembering our handy rule of thumb, we're looking for values 2 standard deviations away from the mean, and when you subtract 2 sigma from the mean, more question that's worth your time to ponder.
The partial derivative of a two-variable function is just the slope. Now, if you combine these partial derivatives and makes them a vector, then a new vector field can be generated. These are the gradient vectors. It is common to plot the gradient of a 3D surface in a plane. The gradient vectors points in the direction of greatest increase of a function. And if you multiply it with -1, then the vector points in the direction of greatest decrease of a function. Imagine a football at the top of a hill. Kick the ball in any direction, it will always follow the path of steepest descent, which is negative gradient. Now, in order to climb the hill faster, just follow the path of steepest descent, which is positive gradient. The partial derivative of a two-variable function is just the slope. Now, if you combine these partial derivatives and makes them a vector, then a new vector field can be generated. These are the gradient vectors.
The biggest barrier you're going to have is pushing through your comfort zone and learning how to write proofs. That's going to be
the biggest hurdle you're going to have. Because once you learn how to write proofs, once you push through that hurdle, you're going to get better. And learning to write proofs isn't like a one-step thing. You don't just take a proof writing class and, oh, I know how to write proofs. You take a proof writing class, you learn the basic structures of proofs, and then you start tackling these new topics. You start learning linear algebra, you start learning number theory, you start learning abstract algebra, topology, advanced calculus, aka real analysis. You start learning these different areas of math, and you start applying those basic proof techniques to those different areas. The biggest barrier you're going to have is pushing through your comfort zone and learning how to write proofs. That's going to be the biggest hurdle you're going to have. Because once you learn how to write proofs, how can you get better at proofs right now? Like right now. There's actually something you can do, and I do this every time I write a proof. And it will make you better at proofs pretty much immediately. Like, it will make you understand things better, it will clarify your ideas, it'll just make you better. So here's the thing. After you write your proof, so once you figure it out and you prove it, and you know it's correct, that's a big one. A lot of times people will prove things and they'll think it's correct. And this is tough. It's hard to know, when your proofs are correct. The best way to know if your proof is correct is to have someone look at it for you. And that's hard. It's hard to find someone who's going to sit there and go through your proof. I mean, if you have a teacher, do it. Go see your teacher and ask them to look at your proof. But if you don't, the next best thing is to find a proof on the internet or in a book and then compare it to yours and then make sure your proof follows the same exact logical steps. So once you know that your proof is correct, here's what you can do to get better at proof writing. You go through your proof and you really think about every step, okay? You try to think about the structure of the proof. Look at your hypothesis, where you started your proof. You started with your hypothesis, your assumption. So like if you're doing like an if-then proof, analyze that part. And then think about what your next step was. After you wrote down your hypothesis, what was your next step? Did you use the definition of your hypothesis? A lot of
Statistical Inference by Casella and Berger. It is hard to understate the value of this book. Even if all someone reads is the first 2 chapters, that would be sufficient for any entry-level position in data science. The problem set is fun and challenging, and you will probably never get through all of it. In my master's program, I'm not sure if we even did half the problems, and that was with 2 semesters dedicated to this book. There are a number of interesting tables, like the table in the back of the book, which shows how many of the popular probability distributions are related. This is a graduate-level textbook. It is a must-have for anyone trying to learn mathematical statistics. The book is heavy on definitions and expects the reader to play with those definitions in the form of applications, derivations, and occasional proofs. Though I have been out of school for many years, I will still pick this book up, pick a section at random, and read it through. It keeps me sharp, and even if I read a section before, I often learn something new on a 3rd or 4th pass. There is a reason this continues
that you should read to improve your statistics skills. Now, just a disclaimer, I have read these books and I found them to be good, but they are not super excellent. So I'm yet to find a book that just blows my mind. The first one is Introduction to Statistical Learning. It's
What have you been up to today? Okay. So, yeah, let's just. I mean, I don't want to learn anything like new. I'm just gonna master the fundamentals. So if you go on NeetCode, there will be like the roadmap thing, right? My plan is to just master the triangle, the first 6 thing, and just like redo the same thing over and over again. I don't wanna. It doesn't matter how much I've done it. You know what I mean? Yeah. Trees and DPs. Yeah, trees and DPs are like kinda important, but yeah, like for now. Yeah, I wanna. So I've done like 40 or something. Let me check. So the blind 75, I've done like 14 out of 75. The NeetCode all, I've done like 34. And the rest of them is like spread out in LeetCode. Uh, 14, yeah. So some of them are like spread out in, LeetCode too. So I've like split it for some reason. That's like the most commonly asked questions. So that's where the roadmap actually comes from. So the roadmap, if you go and check the roadmap, it's just like every question is like the blind 75 question. Eventually, I think LeetCode 150 should be the goal. I don't think there's like any use in doing 250 problems, like ever. So I'll start like a timer. So let's do like a 90-minute time block where I mean, do you want me to recommend you any like specific order? The way you need to like go. So I think, yeah. So we'll like do like what do you call? Like we'll discuss like what to do before. We'll like do our study session individually and come back and discuss what we did wrong, whatever. Okay. So I think the best way to approach is obviously like array and hashtags. Hashing. I think the first, I think if you go, let me see. If you go NeetCode all, they should like give you only the easy questions. So if you like only like sort between the difficulty, and I would say like in the you should like kind of like the selection of like actual sums is like more important than completing it, if that makes sense. So I would say like obviously follow the roadmap at the beginning, but when it gets like a little bit more difficult or easy, you could just like watch the solution, right? And like and like usually like so some of the topics like keeps reappearing, right? So you'll understand like when you like do a couple of sums, like some of the stuff that I'm saying might be too retarded. Yeah, if you like sort it with the easy, with the difficulty thing, it is roughly the thing that is like the most easy. I mean, the progressive way to like go about it. What is it? Yeah, maybe. But you wouldn't have like the lot of mediums. You know what I mean? I'll like send you over a thing, by the way. Give me a second. So this guy gives like the theory behind like everything. So before you even like start to like do anything with the coding, I think this videos might be useful to like get a understanding. So I'm pretty sure you know you're following like the NeetCode guy. So you should be also checking out this guy, if I could find him. Yeah. I think this video is like a good start, I think. Are you able to see it? Yeah. So this guy gives like the conceptual, bigger picture of things. And the good thing about NeetCode is when you go into the sum, like let's say you spend like 5 to like 10 minutes trying to like solve it, you could just like go to the solution and there's a YouTube video right there. You could just click and watch the YouTube video and like get like some sort of a hint and come back. So I think NeetCode does this thing where it's like he explains the video. I mean, he explains the sum, the question, and the solution, and he quotes it right at the end. So you can like stop anywhere between explaining of the question or explanation of the answer or actually typing out the code. So it's always, you can always like stop anywhere between them and go back to coding. Okay, I'll mute myself and you can mute yourself. I'll start the timer or something. I don't know. And if you need anything, just like let me know, okay? sorting. So if you're given a string S, the score of a string is defined as a sum of an absolute difference between ASCII values and adjacent character. Return the score S. Length of S, okay, for I in range of length of S would be equal to yeah. What happened? No, it's just like the entire list of like every single thing from everywhere. Yeah, total. The total will be 150. Yeah. Mediums. Yeah, yeah. But the thing is, the mediums are all like builds off of the easies. You know what I mean? Like, so if you, yeah. Yeah. That'll be good. But yeah, you'll see what. Yeah. Yeah, that's what I mean. Some of the medium questions is not actually like medium. It's actually like pretty difficult. It's actually borderline hard. So you'll. Yeah, exactly. Yeah, that's the thing. Like, if you. Yeah. If you can't like solve within like 10 minutes, there's no shame in watching the video, and not like watching it completely. I wouldn't recommend it, but watching the explanation part and coming back and trying it, watching the actual like code a little bit, coming back and trying it. You know what I mean? Okay. if it is equal, fine. So let's take this.
Let's solve LeetCode 3, longest substring without repeating characters. We're back to a classic LeetCode problem, the third one. So this one's pretty simple. We're just given a string and we want to find the longest substring without any repeating characters, right? Like how these three don't have any duplicate characters, A, B, C. This one has two A's, so this would not count as a substring without repeating characters. And we only need to return the length of this substring. So the first idea that comes to my mind at least is to just check every single substring, check if it has any duplicates. If it doesn't, then we're just going to take the longest one of those strings and return the length. So how would that algorithm run? Okay, first we'd start at A. We want to get every single of them going, even with any repeated characters. So let's actually just do that. Let's make sure that our window, right, our duplicate, we have two sliding window until we no longer have duplicates. So I'm going to, our substring runs from here, from the B, it's still only length 3 or not. So we're going to check our window from the left and we remove is the B, so now we're done. So now our sub B. But notice we still have two B's in our substring. So we got to remove another character. We have to remove this B. So now our substring runs from C to B. So we are valid again, but now our substring is only length 2. Next, we'll get to the last B, last character we're adding, and see, yep, it's a duplicate again. And don't forget that as we're removing these characters from the left, we're removing a C. We're not just removing it from our window, but we also have to remove it from our set, because our set is going to correspond to all the characters in set. Because of our turn, this, well, we were case it was obvious get a set to make sure we have all the characters in our window, so I'll call it character set. And we're going to do a sliding window, so we need 2 pointers, a left pointer and a right pointer to determine our sliding window. Our left will be initialized to 0, and our right pointer is going to continuously be changing as we visit every character. So I can just use it in this for loop. So the right pointer is going to go through every single character. Now remember, if we get to a duplicate character, that means we have to update our window and our set. So while this character that we just visit at the right pointer, S of R, is already inside.
Yo. How's it going? Alright then. Did he do it? Okay. Well, you're doing it in C# too, right? What question is it? Oh, contains duplicate. Okay. Yeah, try to do a medium sliding window problem. I got 2 out of the 3 test cases, and yeah, sliding window. I think my logic was like kind of good, but I think I should have used. I think I was trying to get fancy and trying to use a stack and a sliding window at the same time, and didn't work out for some reason. What is it? Yeah. I've done I've done like pretty much like everything on the top 6 thing. It's just like I have to like do some of the mediums, which are like a little bit more. I wouldn't say difficult. It's just like builds on each other basically. So when if you go on the roadmap thing, like if you see the linked list kind of builds on tree, and binary search kind of builds on tree. It's not actually true, but it kind of does, if you know what I mean. 2-pointer definitely like builds on list. So every topic, every medium topics like is basically like we need to implement a 2-pointer inside of a linked list. You know what I mean? So that's how everything kind of basically works. Like even stack, you would think stack is something different. It's just like basically an empty array that we call it a stack. You know what I mean? Yeah, exactly. Yeah, absolutely. Okay, I'm gonna do one more. What is it? Like what, stack? Does it like follow the FIFO, first in, first out thing? So automatically like does the logic itself. It's like a you kind of like append the list outside the for loop, and then you make it iterate over the for loop on the list. Yeah. Dot pop, dot append. The thing is, linked list trees, graphs and DP are like different, like completely different data structures. You need to like, you know what I mean? I'm sorry. No, not DP. Graphs, trees, and linked lists are like completely different compared to like what we do usually. Everything else is like basically an algorithm, right? That's where like data structures and algorithm kind of comes from. Yeah, exactly. Yeah. That's why I don't like. I mean, graphs are like kind of non-negotiable if you want to do anything in machine learning or even in data science, I guess. But trees, I just don't like it at all. Yeah, kinda. But for me, I do a lot of math. So the bottom one, math and geometry, I've done some couple of sums on it. Okay, I'm gonna do one more and let's see. Okay. Yeah. Nice job attempting a sliding window. Your current code uses a stack and a counter, but the logic is tangled, can miss cases. A cleaner standard solution uses a sliding window with a set or a map that can track. Okay, the sliding window is an alphabet case. Sliding window, keep a pointer as and maintain the set of character in the sliding as RS. if s is not set in the extent of the SR max length, okay, code. Max length of the substring left right seen for right in range of length while. Yeah, I don't understand the while thing. Fucking bitch. Character replacement. So you're given a string S consisting only of uppercase English letters, English characters, and an integer k. You can choose k characters to the string and replace them with any upper class character. You can, okay, replace them with only any uppercase character. After performing a k-most replacement, return the length of the longest substring which contains only one distinct character. What am I doing? What are we doing? After performing the k replacements, return the, okay. Bro. So I need to find so let's say
Hey everyone, welcome back, and let's write some more neat code today. So today we're going to solve longest repeating character replacement. And so this is another problem from that blind 75 list. So we are going to be one step closer to completing the entire list. The link will be in the description to this spreadsheet if you do want to take a look. And hello to the 6 people that are currently viewing the spreadsheet right now. You're going to be in the next video. But okay, so let's get into this problem because it's another pretty fundamental problem that's really good to understand. So we're given a string s and a single integer k, and so basically they tell us that we can choose any of the characters in the string and change it to any other uppercase English character. So in this problem, every character in the input string is going to be limited to uppercase English characters, and we know that there's 26 uppercase English characters from capital A to capital Z. And so basically we can perform a replacement on any of the characters at most k times. So we are allowed to replace k different characters in the string to any other character we want. And what we want to do is return the length of the longest substring containing the exact same character we can get at. After performing at most k different replacements. So we just want to return that length. We don't actually have to make those replacements in the input string. So in this case, when we take a look at the input string, we have AB, and we're allowed to replace 2 of the characters. So what's the longest substring we could get with the exact same character? Well, we could replace one of the B's. We could basically replace both of the B's with a capital A, and then we get 4 A's in a row, which would give us an output of 4. And we could technically also do the opposite. We could replace the A's with capital B's, and that would give us the exact same result, a length of 4. So I'm going to show you how you can solve this problem in big O of n time, and technically it's going to be big O of 26 multiplied by n, which we know is also reduces to big O of n, but there's actually technically an easier way to do it, or at least a more simple way to do it, which is just going to be a flat big O of n. We don't even need this 26 constant, but so let's say we're given an input string like this, and we're given a k value. Now, the most brute force way would just be check every single window to characters we want to equation. We're going to have to add a selected by the count of. And if that does happen, right, let's say we took B and then at position R, we're going to increment the count of it. We're going to take 1 plus whatever the count currently was, count.get this character. And if the character doesn't exist in our hash map, we're just going to return a default value of 0. That's what this function is doing. And so what we're going to obviously do is update our result, right? And we want to set the result equal to the max that it's ever been and set it basically equal to the size of the window. We can get the size of the window. So we're going to take the max of result and the size of the window. The size of the window can be gotten with right minus left plus 1. But before we do this, before we update the result, we want to make sure that the current window is valid. So what I'm going to do is basically say while, and I don't think you'd actually need a while here. You could just do if, but I'm just going to do while just because. So while the window is not valid, and we would know that by taking the length of the window, which we have down here. So I'm just going to copy and paste that. The length of the window subtracted by the count of the most frequent character, which can be gotten with max of count dot values, right? We're basically going through the entire string. Then we can just simply return our result. And as
Busy agama.
சிஸ்டம் வைக்கிறதுக்கு உனக்கு வாங்க
வைங்க. என்னது
சிஸ்டம் வைக்கிறதுக்கு டேப் வைக்கிறதுக்கு படிக்கிறதுக்கு பார்க்கணும்.
Fucking bitch.
Hey everyone, welcome back, and let's write some more neat code today. We're given an n by n matrix, so this time it's a square matrix for sure, representing some image, and we want to rotate that image by 90 degrees clockwise. And we are required to do this in place, so we cannot allocate more memory. We can't just make a copy of the matrix and rotate it like that. So the challenge here is definitely doing it in place. You can see that they had a original matrix like this. What they did is they took the 1 and put it over here, so 90 degrees. Basically what they did is took this entire first row and moved it into the rightmost column, right? And so they did that by moving this over here, moving this 2 over here, moving the 1 and just this like this. It's still technically a square, you know, if you turn your head a little bit, but this is what we're doing. We're rotating this. So this 4 is of course going to be moved over here to this 2, and before we get rid of the 2, we want to save it and move it over here. We're doing, and before rotating it will just be the exact same. So let me show you the general algorithm to solve this problem. We're going to do this in n squared time, meaning we only have to look at each cell in the matrix once. Remember, the dimensions are n by n. And we don't need any extra memory, so the memory complexity is going to be constant. We're doing this in place in our given matrix. So I like to set some boundaries. So we know that this is our left boundary and this is our right boundary initially, because we're going to rotate the outermost layer first, right? The outermost square, and then we're going to move inward, right? We're going to do the inside of the matrix. And the top boundary I'm going to place over here because that's the top. Remember, the origin over here is 0 by 0. This position is 3 to 3. It goes like this, and as you go down, it increases. And the bottom boundary is going to be down here. So immediately we're going to start the rotation. Now, how is the rotation going to go? Well, let's start at the top left because it's the easiest, right? We know that this is the general rotation that's going to take place, right? Because we're going clockwise, and then we're going to do that, right? And we know we're going to keep doing that with every element in the top row. So we did the first element in the top row, then we're going to rotate the second element in the top row. And how is that going to look? Well, it's going to be pretty similar. So since this was the second position in the top row, we're going to move it to the second position in the last column, right? So in this column, we're going to rotate this one to this position. So the second to last position in the bottom row. The main thing to notice though is that this is offset by 1. This is offset by 1 from the top. This is offset by 1 from the right. And so the position that it's moved to is also going to be offset by 1
going from the bottom, which is where, over here. And so as you can see, we have one last rotation to make, right, with square. We're actually not doing 4 rotations for the outermost layer. We're doing 4 minus 1 rotations. We're doing 3 rotations, right? So even though the outermost layer was n by n, we actually did n minus 1 rotations, right? So we did 3 rotations. And let's say after we complete the outermost layer, right? So once we do that, then we know that we actually have an inner matrix. An inner matrix that we have
Yep. How are you doing? You done? Which one? Let me see. Let me see anagram. How do you do it? So I think, correct me if I'm wrong. So I think the way you do anagram. Fuck. Hey. You use like a hash map, right? You iterate over then and you append it to the hash map and check if it's there. Okay. Oh, must be like a just in time thing. I don't know. I think in Python you could just like compare the actual index of both of them. No. I'm sorry. The length. I'm sorry. What the fuck am I saying? You could just like sort it. You could like sort it and check. Is it? Let me check. Oh yeah, it does. Do you guys have that in C# where you can just sort things? C#. Oh, you write that every day? Bro, it looks so big. Bro, C++ is like more simple. It looks more simple. I mean, the syntax looks cleaner, for sure. Yeah, compared to like C#. Okay, maybe in like game dev production might be different. Yeah, I did. What? C, I mean, C is kind of like built on. I mean, C++ is kind of built on C, isn't it? I'll send you another website. This is Elite Ball Knowledge. I think this is. I don't know if this is accurate for game dev, but it's for like it's like a Chinese ripoff for like they snitch on like all of the job. What is it? Yeah, there's like a. It basically exposes like what questions they're asking in like particular companies on their hiring. You do need to like translate. Yeah, you do need to like translate it with your thing. So yeah, if you go like whatever Nintendo or something, they have like things like how to get referral, compensation, workplace discussion, and all of that. It is usually for like lead code, what kind of questions being asked and whatnot. But I guess other features are kind of useful too. Bro, they're so fucking cheap. I know. I don't know. I've been looking into like so some of the augmented reality stuff in machine learning. I think that kind of like overlaps with like some gaming too. They did like AI for like game development or something like that, where you can like get an image and you can kind of like make a game out of it. Have you seen it? Yeah, something like that, yeah. It's been... Yeah, exactly, yeah. Yeah, I know, yeah. I think, yeah, it's Google Genie 3, I think. Fucking crazy though. Could be. Like, what do you mean? I didn't hear you. Mm-hmm. Mm-hmm. Mm. Do you use OpenGL? You use OpenGL, no? No? Okay. Okay, okay. Hmm. That's like 2 mathematics, isn't it? Because there's like a lot of overlap with data science and machine learning with that, because it's linear algebra, calculus. Yeah. It's linear algebra, calculus, somewhat probability here and there. I mean, obviously geometry, the main one. Geometry and a little bit of physics. Okay, we'll call in tomorrow and we'll see. We'll do another batch of questions. Yeah. You're gonna solve one more. Okay. I'll send some stuff when I get some time. Alright, bro. See you. Bye. fucking Bro, I need to get one more. Algebra and trigonometry.
In 2022, when I...
Fucking nigger.
I was just 16 years old, I sat the Edexcel Level 3 Algebra Award. This was an exam focused purely on algebra, with no silly statistics or real-world applications. I scored something like 96%, which I was absolutely chuffed with, but then I was quite annoyed to find out that there wasn't a Level 4 Algebra Award. Clearly, this is an absolute outrage, so today I'm going to be giving you the 7 levels of algebra, and you can tell me in the comments which one you think you are. Level 1, the good old days. This was when algebra was simple. The teacher would give you a problem, and your job would be to find the missing number, which was usually called x. If you got it right, then you get a sticker to stick to your shirt to show everybody how smart you are, but if you got it wrong, then your teacher would take his shoe off, smack it against the desk, and then threaten to beat you with it. The good old days. Level 2, intermediate algebra. Here you learn about graphs, quadratic equations, systems of equations, and polynomials. I remember in primary school, I was always curious about quadratic equations because it sounded really complicated and that only people with big brains could actually do it. But when I got older, I realized that most of the time, the teachers are just going to make you plug numbers into this big long equation that they're going to force you to memorize. So it's not really about being intelligent, it's more about just being able to memorize an equation. But if you're a base, complete the square filled sigma male like me, then you'll never have to memorize a quadratic formula because you'll just complete the square every single time. And if you prefer to just plug numbers into formulas that you've memorized, then you should probably do a subject that requires less intelligence like physics. Level 3, you can now find x. On this level, you'll know all you need to know about functions, higher degree polynomials, and you can probably do differentiation and integration too. You may have also learned the fun stuff like how to find the sum of all integers from 1 to 100 in a matter of seconds using summation formulae, and of course, at this level, you can do level 3 algebra award. Most people will have already stopped by now, which is why, generally speaking, most people don't understand truly how deep the algebra rabbit hole goes. Level 4, linear algebra. Now you can not only solve systems of equations with 2 unknown variables, but you can also solve them with 3, 4, and even 7 using matrices. Basically, you are completely useless unless if you have 3 separate bank accounts with 3 different fixed interest rates and you don't know anything apart from the total over the past 3 years of all 3 bank accounts, and you want to find how much is in each individual bank account. You know, that common problem that we're all faced with on a day-to-day basis. While your skills are almost completely useless, at least a ring is still something that you give to a woman you want to marry, and a field is something that a farmer uses to grow crops. Level 5. So basically, this is algebra, and you've learned this bit. Now, a ring is an algebraic structure with 2 binary operations. You can't quite remember what a woman is or what it has to do with rings, and you can't remember the last time you've seen a real field because you don't really go outside much anymore. In terms of algebra, a field is a commutative ring in which every non-zero element has a multiplicative inverse, and if that sounded like just a bunch of random words to you,
So let's talk about algebra, and I mean really talk about it, like the whole story, from the very beginning all the way to what we know today. Because here's the thing, most of us were forced to memorize formulas and solve for x in high school, but nobody ever told us that algebra or stories in all of We're talking thousands of years, multiple civilizations, international drama, duels to the death, and some seriously brilliant minds who changed how we think about pretty much everything. Before we jump in, I need to set something straight. When you hear the word algebra today, you probably think of equations with x's and y's, right? Maybe you remember solving quadratic equations or factoring polynomials. But algebra hasn't always looked like that. In fact, for most of human history, algebra looked completely different. There were no symbols, no letters, no elegant formulas written on a chalkboard. Just words, lots and lots of words. Think about it. Imagine trying to solve an equation without being able to write x plus 5 equals 8. Instead, you'd have to say something like, the thing plus 5 equals 8, every single time. That's what early algebra was like, and somehow, people managed to solve incredibly complex problems using this method. So, where do we even start? Well, let me take you back, way back. We're talking ancient Babylon, around 1900 years before the Common Era. The Babylonians are living in what's now Iraq, and they're dealing with practical problems. How do you divide land fairly? How do you calculate interest on a loan? How do you figure out how much grain you need to store for winter? These weren't abstract math puzzles. These were real-world problems that affected people's lives. And the Babylonians figured out that they could solve them using what we'd now call algebra. They developed methods for solving equations, even quadratic and cubic ones, and they wrote everything down on clay tablets. These tablets survived thousands of years, and when archaeologists dug them up, they found something amazing. One of the most famous is called the Plimpton 322 tablet. This thing was created somewhere between 1900 and 1600 BCE, and it contains a table of what we now call Pythagorean triples. That's way before Pythagoras was even born, by the way. The Babylonians were working with advanced mathematics that wouldn't be rediscovered in Greece for over 1,000 years. But here's what's wild about Babylonian algebra. They didn't care about exact solutions. They were happy with approximations. They used something called linear interpolation to get close enough answers for practical purposes. And you know what? That makes sense. If you're a merchant trying to figure out how much to charge for grain, you don't need 12 decimal places. You just need something that works. The Babylonians also developed what we'd call algebraic operations. They could add equals to equals, meaning if you have two things that are equal, you can add the same amount to both sides and they stay equal. They could multiply both sides of an equation by the same thing. They could manipulate equations in ways that seem obvious to us now, but were absolutely revolutionary back then. Meanwhile,
Chat, how's it going? Algebra is not easy, but it can be broken down step by step and explained in such a way that even little Timmy here can understand. And if you're anything like little Timmy, you are worried that you don't quite know your polynomials, conics, or functions, which happens to be exactly what I'm going to warble about for the next 15 minutes. Polynomials. Poly simply means many, and nomial means name or term. Terms in maths
It really is strange because if you think about it, Calculus 1 and Calculus 2 and Calculus 3 typically all use the same book. So if you go to college and you take Calc 1, you buy this book. Nowadays, you usually get the ebook, but you can buy the physical book. It's usually really, really thick. And it covers the material for all three courses. And so Calc 1 covers some of those chapters. And then when you go to Calc 2, you just cover different chapters. So you might wonder, why are they so different? And they are. Calc 2 is considered to be way harder than Calc 1 and harder than Calc 3. It's just the topics are harder, the techniques are more sophisticated, and it's just a harder class. I've taught hundreds of classes over the years. I've taught a lot of Calc 2 classes. In fact, I actually taught Calculus 2 before teaching Calculus 1, which is kind of unusual. And I've seen it. I've seen people struggle. I've had students that get A's in Calc 1, and then when they get to Calc 2, it's like, game over. So I think it's just the subject is just more involved. You know, in Calc 1, you start with limits, then you do some derivatives, then you do some basic integration. In Calc 2, you raise the bar. You still do some limits sometimes, but you do way more integration. You do some applications of integration. Then you do infinite series and a couple other things as well. So the level just raises the level of sophistication. And then in Calc 3, you kind of go back to Calc 1 at the beginning, and you extend those single variable concepts to
This is me. In my first year of college, I took multivariable calculus, a course that many of you may be familiar with. When I was taking the class, my roommate let's call him Ari, was a physics and CS double major. He had taken the course before, so he offered me these words of wisdom.
The way that multivariable calculus all comes together at the end is just amazing.
Now, let me tell you, even after taking the class, I had absolutely no clue what Ari was talking about. Despite all of the long nights of double integration and essay writing, true story, we wrote essays for calculus. I still didn't get it. The problem was, I understood all the theorems and concepts individually, but I couldn't see how they were all related. And I think that's a boat that a lot of students are in. Seeing connections between things is all about perspective. I can show you thousands of pictures of the Earth, but you'll never gain the perspective that astronauts have when they look down on our planet from thousands of miles in space. What Ari was describing, this idea that multivariable calculus all comes together somehow, was a perspective. And in this video, I'm going to present that perspective to you by building multivariable calculus from the ground up. So let's get into it. I'm going to talk about 5 different theorems here. The fundamental theorem of single variable calculus, the fundamental theorem of line integrals, Green's theorem, Stokes' theorem, and the divergence theorem. Theorems 1 and 2 are very similar. 3 is actually a special case of 4, and by the end of the video, you'll see how all 5 of them are really the same thing. As we build up from one theorem to the next, we'll work with higher dimensional objects and spaces. As a disclaimer, I'm not going to spend much time rigorously proving these theorems. It's not important for this video, since we just want to see how they're all related. Let's start with the fundamental theorem of single variable calculus. The formula for this theorem can be written like so. What this is saying is that the difference between the value of a function f at x equals b and its value at x equals a is equal to the integral of its derivative from the bounds x equals a to x equals b. To build up calculus from the ground up, I'm going to break this formula down step by step. We can write the derivative of f in prime notation as shown, or in Leibniz notation like this. Leibniz notation essentially writes the derivative as a quotient, df divided by dx, where df is a very, very small change in f, and dx is a very, very small change in x. Mathematically, derivatives are not actually quotients, but writing it this way can help us understand the geometric intuition behind this formula. Let's consider the graph of f versus x. Here, I just chose f to be a random curve that is both continuous and f of f versus. We can write the derivative of f in prime notation as shown, or in Leibniz notation like this. Leibniz notation essentially writes the derivative as a quotient, df divided by dx, where df is a very, very small change in f, and dx is a very, very small change in x. Mathematically, derivatives are not actually quotients, but writing it this way can help us understand the geometric intuition behind this formula. Let's consider the graph of f versus x. Here, I just chose f to be a random curve that is both continuous and differentiable along the interval a, b. What that means is relevant for proving this theorem, but not too important for our intuitive explanation. If we look back at our theorem in Leibniz notation, we can sort of pseudo-cancel the dx's to get just the integral of df from a to b. Mathematically, you can't actually do this. df dx is not a quotient, but an operator ddx acting on f. But we'll write our formula like this just to help develop intuition. Remember that df is a very, very small change in the value of the function f. Infinitesimally small, in fact. Graphically, this would correspond to a vertical movement from one value of f to another. So we understand what df is. Now let's check out the rest of this truncated formula. Integrals can also be thought of as infinite sums. In our case, this integral means we're adding up an infinite number of infinitesimally small differential components df. So this integral is really telling us to add up all of the infinitesimally small changes in f from x equals a to x equals b. The sum of these tiny changes in f from a to b is just the total change of f from a to b. And so we can see that the integral of df from a to b is the same as the difference between the value of the function at b and its value at a. Now let's rewrite our theorem the way it was originally written with Leibniz notation. Just as df was an infinitely small change in f, dx is an infinitely small change in x, which would be a very small step in the horizontal direction on our graph. You might have heard that df dx is the slope of a tangent line to f at a given x. This makes sense. df is our vertical rise and dx is our horizontal run. And if we divide rise over run, we get the slope. To get df, we just have to multiply that slope by the corresponding dx at a given point. So really, when we're taking an integral, we're summing all of the products of the slopes times their infinitesimal runs from a to b, which is the same as summing all of the infinitesimal rises from a to b. The reason we have to consider each infinitesimal dx is that the slope, df dx, changes slightly at each value of x. When we describe the fundamental theorem in this way, we've essentially broken down the ideas of integration and derivation completely. Integration is the infinite summation of infinitely small components, while derivatives are simply slopes. Multiplying a slope by an infinitely small run gives us an infinitely small rise, and taking the infinite sum of all the rises gives us the total rise. And that total rise is the net change of our function. I'll say it one more time just for emphasis. Multiplying a slope by an infinitely small run gives us an infinitely small rise, and taking the infinite sum of all those rises gives us the total rise. And that total rise is the net change of our function. So that was a lengthy, intuitive description of the fundamental theorem of single variable calculus. We can, of course, make this description even more concise, and that will be of great use to us in understanding how multivariable calculus all comes together. But it also means we have to make a sacrifice. Unfortunately, in higher dimensions, this simplified description of integrals and derivatives doesn't quite hold up. Our derivatives aren't always going to be slopes, and our integrals aren't always going to be infinite sums along axes, but instead infinite sums over new, weirder shapes. We'll get into what that looks like, but for now, this just means that it's better for us to describe the fundamental theorem of single variable calculus not with the dimensionally restricted concepts of slopes and sums, but with the more abstract ideas of derivatives and integrals. So with that, let's put this formula into words. The integral of the derivative across the bounds is equal to the original function at the bounds. Keep this sentence in the back of your mind. We'll put it aside just for a moment in our formula dictionary, a set of conversions of calculus formulas to plain English. We'll continue to add to this dictionary over the course of the video and get back to it near the end to answer our overarching question. Now, let's discuss line integrals. From the name, they suggest we are taking the integral over a line. But what exactly does that look like? Well, for our purposes, we're going to be looking at line integrals of vector fields. You can think of a vector as an arrow with a magnitude or size and a direction. Vector fields are kind of like functions that output a vector to each point in space. The line integral of a vector field over a curve C is calculated in a similar way to the integral of a regular function. For the 1D case, we multiply something in the fundamental theorem that something functions that output a vector to each point in space. The line integral of a vector field over a curve C is calculated in a similar way to the integral of a regular function. For the 1D case, we multiply something in the fundamental theorem that something was the slope of the tangent line by tiny changes in x to get a tiny change in y, and add up all those tiny changes in y to get the overall change in y. For the case of our vector field, our tiny changes in x are now the vector derivative of our curve C. C is a vector-valued function, written as r of t, which is similar to a vector field, except now each point on the curve C is defined by a vector that points in the origin to a point on C. Because C is vector-valued, it defines the x and y coordinates of its points in terms of a new variable t. So we have derivatives in both the x and y directs curve or output a vector to each point in space. The line integral of a vector field over a curve C is calculated in a similar way to the integral of a regular function. For the 1D case, we multiply something in the fundamental theorem that something was the slope of the tangent line by tiny changes in x to get a tiny change in y, and add up all those tiny changes in y to get the overall change in y. For the case of our vector field, our tiny changes in x are now the vector derivative of our curve C. C is a vector-valued function, written as r of t, which is similar to a vector field, except now each point on the curve C is defined by a vector that points in the origin to a point on C. Because C is vector-valued, it defines the x and y coordinates of its points in terms of a new variable t. So we have derivatives in both the x and y directions, which together sort of make a derivative vector, r prime of t. We take this derivative vector and multiply it by the vector in our vector field at a given point. Except we can't multiply two vectors, so instead we take their dot product. Adding up all of these dot products at different points along the curve C gives us the final value of our line integral. Mathematically, this idea can be written like so. Our something is now a vector field. Our tiny changes in x are now derivative vectors of C. Our tiny changes in y are now dot products. And instead of adding all the tiny changes in y, we add up all the dot products to get our overall line integral. The bounds a and b are now the endpoints of our curve C. The x and y points inputted into our vector field are often just written as r of t, because those are the points on our curve C. Oftentimes, we can also truncate this derivative vector to just dr, to better represent the idea that this is a derivative vector. And finally, we usually don't write the bounds of our integral as a and b, but instead just write c at the bottom, indicating to take the integral over the whole curve C. If this description was confusing, that's because I glossed over a few important details, but don't worry about that for now. I'll make a video later explaining line integrals in much more depth. For now, let's take this idea of taking the integral over an arbitrary curve for granted and examine the bigger picture. The reason we care about line integrals of vector fields is that the gradient of a regular multivariable function is a vector field. Well, then what the heck is a gradient? The reason we care about line integral of an arbitrary curve for granted and examine the bigger picture. The reason we care about line integrals of vector fields is that the gradient of a regular multivariable function is a vector field. Well, then what the heck is a gradient? When we have a function with multiple inputs, a multivariable function, we don't just have one derivative. We have many partial derivatives. Derivatives of the function with respect to each input variable, assuming all other inputs are constant. And when we compile all of these partial derivatives as a vector to make a vector field, we get the gradient. The gradient points in the direction of greatest change of the value of our function. You can think of each of these partial derivatives as a vector to make a vector field, we get the gradient. The gradient points in the direction of greatest change of the value of our function. You can think of each of these partial derivatives as moving along the axis of that respective input variable. This would be moving along the x-axis, this along the y-axis, this along the z-axis, and this along the w-axis. If we have too many input variables, it becomes impossible to visualize. So for demonstration purposes, let's stick with just two input variables and one output. This way, we can graph our function in 3D space, and we can graph its gradient in 2D space. Let's use the function f of xy is equal to x squared plus y squared to demonstrate gradients. If we take the gradient of this function, we get the following vector field, where each vector in space is defined by twice its horizontal x-coordinate and twice its vertical y-coordinate. Now, let's draw some random curve C in our gradient its vertical y-coordinate. Now, let's draw some random x-coordinate and twice its vertical y-coordinate. Now, let's draw some random curve C in our gradient field. Vector in space is defined by twice its horizontal x-coordinate and twice its vertical y-coordinate. Now, let's draw some random curve C in our gradient field and try to find its line integral. Let's make this curve the line segment of y equals x squared, going from 1, 1 to 2, 4. Once we take the line integral of our gradient field over this curve C, and the details of this are not particularly important, we find that our line integral is 18. Interestingly, if we plug in the endpoints of our curve C, 2, 4 and 1, 1, into our original multivariable function f, we get 20 and 2. And their difference is the same as our line integral. This, ladies and gentlemen, is a fundamental theorem of line integrals. Written formally, the theorem looks like this. Let's put this integral. This, ladies and gentlemen, is a fundamental theorem of line integrals. Written formally, the theorem looks like this. Let's put this equation into words, just as we did with the fundamental theorem of single variable calculus. The integral of a gradient over the integrating curve is equal to the original function at the curve's endpoints. Let's add this to our formulas dictionary. For the last 3 theorems, I'm not going to go into as much detail on the specifics as I did for the previous 2. There are plenty of incredible videos out there visualizing these theorems in different ways. Instead, I'm going to focus on the bigger picture so we can get an answer to our initial question. How does multivariable calculus all come together? Now let's talk about Green's theorem. The formula for this theorem looks like this. Looking at this for the first time, it can be difficult to understand exactly what's going on here, especially if you're not familiar with double integrals. Let's break it down. For this theorem, we're still just working with the 2D xy plane. On the left side, we have a line integral over a curve C, just like before. Except now, instead of finding a dot product of a vector field and a derivative vector, we multiply each component of the vector field by the differential component in its respective direction. Mathematically, it's the same operation, just written differently. We multiply the horizontal part of our vector field by a differential movement in the horizontal direction along C, and the vertical part of our vector field by a differential movement in the vertical direction along C. Then, we add up all those products over the entire curve C. This circle here means that our curve is closed, and that we want to take a line integral over the whole closed curve C. On the right side, we have a double integral over an area D. This area is enclosed by our curve C, and we're taking the integral of this weird combination of partial derivatives. It turns out that this combination of partials can be interpreted as a measure of how much a vector field curves or curls. You can think of this as a tiny circle vector existing on a differential area component like this. All the double integral says is that we need all of these tiny curls times a tiny area component they are on in both the x and y direction separately, which is what it means to integrate over an area. It's basically just 2 consecutive integrals. First, take the integral with respect to x, get some result, and then take the integral of the result with respect to y. The conceptual idea behind Green's theorem is that adding up all of these little circles of a vector field inside an area is the same as taking the total curvature of the vector field along the shape's boundary. Going back to the raw equation, we can put it into words, just as we did with the other 2 theorems. The integral of the derivative over the integrating area is equal to the integral of the original function over the boundary curve. Important, the integral divergence theorem can be written like so. On the left side, we have a double integral over a surface S. On the right side, we have a triple integral over a volume E.
Here are the top 10 most important things to know about calculus. Must know number 1, Newton's quotient. To be able to fully understand calculus, you're you're going to have to understand the logic behind Newton's quotient and how you use it to find the derivative of a function from first principles. Let's do an example where we calculate the derivative from first principles of f of x equals x squared minus 2x plus 4, and then we'll use the derivative to evaluate f prime of 4. Now, the derivative of a function is an equation that can calculate the slope or instantaneous rate of change of a function at a single point. I'll use this diagram that I've sketched of this f of x function to help explain this. Let's say for this function f of x that I was interested in finding the slope of it at a single point at some x value. Let's put the point right there. I could label the coordinates of that point, point x f of x. The slope of the function at that single point can be visualized by me drawing a line that is tangent to this function at that point. The slope of this tangent line represents the slope or instantaneous rate of change of f of x at that point. But the challenging part of this is how we find the slope of a line where we only know one point that's on the line. Slope is usually calculated using 2 points and then finding their change in y and then dividing that by their change in their x values. So what we could do is pick another point that's on this f of x function. I'll put the point right here. And let's say that that point is h units to the right of the original point. So its x coordinate would be x plus h, and its y coordinate would be the value of the function at x plus h. And it would be easy to calculate the slope of the line that connects those 2 points. We can find the slope of that secant line just by doing the change in the y coordinates, f of x plus h minus f of x, and then dividing that by the change in the x coordinates, x plus h minus x. And those x's would cancel out, and in the denominator we'd be left with just an h. Now the slope of that secant line does not match the slope of that tangent line. We can make it a better match or a better approximation by moving that point closer along the function to the original point we want the slope at. So we can make the h value, which stands for the change in x, we can make it smaller. So let me zoom in to show you how that would work. If I put the point right here and then found this secant line, notice that that secant line more closely matches the slope of the tangent line. So the logical thing to do to get the best approximation for the slope of this tangent line is to move this point infinitely close to the point we want the slope at. And we have a notation for that. F prime of x. This apostrophe means a lot. It means it's the equation of the derivative, which means it's finding the slope of the tangent at a point. It's the instantaneous rate of change of the function at a point. And to find that, what we want to do is find the limit of the secant slopes, so of that formula, as the change in x, which we call h, approaches 0. So this just communicates that as this point moves infinitely close to the point we want the slope at, the slope of the secant line approaches the slope of the tangent line. And now let's use this formula to find the derivative of that specific f of x function. So f prime of x equals the limit as h goes to 0 of f of x plus h to evaluate a function at x plus h. I need to sub x plus h in for both of the x's into the function. And then Newton's quotient tells me that I have to subtract f of x, so I need to subtract that function. And that all needs to be divided by h. Now this limit is in indeterminate form right now. We can't do direct substitution yet, but we can expand the numerator, collect our like terms, and get this out of indeterminate form. So I'll do x plus h all squared. I'll distribute the negative 2 to both terms, and I'll subtract all 3 terms of f of x. And now let me zoom in so we can see what we can simplify here. X squared minus x squared, those cancel out. Negative 2x plus 2x equals 0, and 4 minus 4 equals 0. Of all 3 terms that are left in the numerator, notice they all have an h. So on my next line, I'm going to common factor out that h. And now I know h is actually not going to be equal to 0 because we're finding the limit as h approaches 0. So I know that I can cancel out those h's, and I'll be left with a limit that is equivalent to double that, so the length would be 2x. And I don't know the relationship between the height, length, and width, so I'll just call my height h for now. And because I'm interested in minimizing the amount of cardboard used, I want to minimize the surface area. So I'm going to need a formula for the surface area of this open top box. Surface area, I just add up the area of all the sides. The front and the back are both x by h. So I would do 2 times x times h to get the areas of those 2 sides, plus, let me look at the right side and the left side, which are both 2x by h. So 2 times 2x times h, plus the area of the bottom of this box, which is x by 2x. And because this is an open top box, I'm not
This video was sponsored by CuriosityStream, home to over 2,500 documentaries and non-fiction titles for curious minds. Let's say you're on a boat moving away from the shoreline perpendicular to it, and after 1 kilometer a very thick fog rolls in, making it so you can't see anything. And let's just say you become disoriented or something happens where you don't remember the direction of the shore. All you know is that you're 1 kilometer away from it. The question is, what's the most efficient way to guaranteed get back to the shore? And by most efficient, I mean the smallest worst case scenario. So whatever method you come up with, find the maximum distance you could drive using it if very unlucky, and that number should be a minimum. Oh, and this ocean is an ideal math lane, so you can determine exactly how far you travel when you do. If you want to turn a certain angle, you can do so exactly. And we'll say you have an anchor and long rope, so if you want to move in a perfect circle about some center, then you can do so. Now, okay, this might not be the most applicable example, but we'll get to those. Give yourself like 33 seconds to think this over, though, while I say that why we have to learn optimization problems isn't really a mystery. It is true that the average person will not need to know most of this stuff in their daily lives, but a lot of you would probably be surprised just how much our lives are affected by the analysis and understanding of maximums and minimums. And sure, problems like minimum perimeter fences or least expensive cans can have applications, but we're gonna get some more motivation here beyond what you're going over in your calc class. Except we're still starting with this more fun, less applicable example, so let's see how that works. For the few people who actually attempted the puzzle, see if you came up with this. First drive 1 kilometer in whatever direction that you think the shore is. It's possible you hit it, but very unlikely. Then move in a perfect circle in whatever direction around that center point, and you are guaranteed to eventually hit the shore. The worst case scenario here is if we go back to our starting location, you move 1 kilometer at an infinitely small angle above the horizontal here, barely miss the shore, and move in an entire circle until you hit it. In this case, you drove 1 kilometer, the radius, plus 2 pi, essentially the full circumference. Now, this is the method most people commented on Twitter when I posted this question, but this is not the best we can do. We can do something else where the worst case scenario is less than 1 plus 2 pi. To show this, I gotta bring the boat closer to the shore. And to summarize the method, we're simply going to drive further in the beginning, I'll say 1.5 kilometers for now, then move along a circle with that longer distance as the radius. What you're seeing here is the worst case scenario, by the way, at least for 1.5 kilometers as that starting distance. Driving that distance in any other direction and then doing a circle will get you to the shore sooner. So whether it's 1.5 kilometers or 2 or 1.4, whatever, all these circular paths have a larger radius and a longer initial straight line drive than before. But we don't have to drive in a complete circle with this method, only part of one. So the question is there some value of d, we'll say, where the worst case scenario path has a length that is less than 1 plus 2 pi? Well, obviously the answer is yes, which is easy to see graphically. The total distance traveled here will simply be d plus the arc, and that arc will have a length of r times theta, where the radius is also d. Then theta is that full angle between the first dashed line, and this other one I'll add in showing where we meet the shore. One of those inner angles would have a value of cosine inverse of 1 over d. So this would be the equation for the total distance traveled in regards to the worst case scenario for any value d. This part here is just r times theta, or 2 pi, the full circle, minus those inner angles. Now if we graph this equation, we get this here. Again, the y-axis is the distance for the worst case scenario path, while the x-axis is d, the length of that first straight line drive. You'll see here at d equals 1 or d equals 1.183 kilometers, the worst case path is 1 plus 2 pi. But anything in between is shorter. And the absolute minimum lies here at 1.04, 6.9.
995. So we can drive anywhere between.
In 1987, the New York Times front page read, "Breakthrough in problem solving." The breakthrough here refers to the invention of the interior point method, an efficient algorithm for convex optimization. And here you might wonder, what is convex optimization and what is so important about it that the headline refers to it as problem solving? And what makes the discovery of
Is differentiation even useful?
Well, me and JJ even used it when we was playing Minecraft last night.
We only had 20 fences left to build an enclosure, but it was annoying because however we built it, the area was always different.
So how do you think we made the biggest area we could?
First, I bet you said that 2 of these lengths plus this width would need to equal your 20 fences.
But wouldn't we care more about the area of that rectangle?
Yeah, the area of the rectangle is what we want to maximize.
And obviously that's length times width, LW.
So at this point, me and JJ rearranged this top equation to get W, and then subbed it into the area equation to get rid of it.
So why'd you get rid of W?
Because now we have A as a function of just L.
And this is way more useful now, because area versus length has this lovely little graph.
So to maximize the area, we want to find this point up here where area is as big as can be.
Haley, we both know that's called a maximum, and it's basically where the derivative of our area function is equal to 0.
Oh, so we need the derivative.
Yeah, so you know what to do.
Say it.
Get out the power rule and differentiate that thing.
Somebody turn that off.
No, I enjoy the zone.
Thank you. Okay, now to find the value of L at this highest point, where the derivative is 0, we can set the derivative to 0 and solve for L.
0 equals 20 minus 4L, so 4L equals 20, L equals 5.
So you get the biggest area when L is 5.
5 fences.
And remember, we had exactly 20 fences, so this width is going to be 10 of them.
Okay, so the biggest space we can build is 5 fences by 10, and it's 50 fences squared in area.
Area maxing complete.
Is differentiation even useful?
Well, me and JJ even used it when we was playing Minecraft last night.
We only had 20 fences left to build an
problem. But as we go through it, I want you guys to keep in mind that all optimization problems can be solved using.
What would you say are the prerequisites for somebody to take the deep learning specialization in terms of maybe math or programming background?
You need to understand basic programming since there are programming exercises in Python. And the math prereq is quite basic, so no calculus is needed. If you know calculus is great, you get better intuitions, but deliberately try to teach that specialization without requiring calculus. So I think high school math would be.
Is Calculus 2 the hardest calculus? Is Calculus 2 the hardest calculus class? Well, let's get right to the point. The answer is typically yes, unless you have like an extraordinary challenging teacher for Calc 1 or Calc 3. Typically, Calculus 2 is the hardest calculus course a person takes in the sequence, in the Calc 1, Calc 2, Calc 3 sequence. And let me explain why, because it's kind of a mystery. If you think about it, most students use one of those really big, thick calculus books for calculus, like the one by Stewart or the one by Larson. So it's the same book for the entire sequence. So why would one course be so much harder than the others? And I think it just has to do with the level of mathematics that's covered. So in Calc 1, you first talk about limits and derivatives, and you introduce those concepts, and you also introduce integration. So you kind of introduce like the skeleton of calculus, right? You've got your differentiation, your limits, and your integrals. Your 3 main things: finding limits, computing derivatives, and computing integrals. Then when you get to Calc 2, you do more of that, but it's more specialized. However, you're still working in one variable. Although you do some stuff with parametric equations, you're still focused on functions of x or functions of y. When you get to Calc 3, you basically go back to Calc 1 and you generalize everything you learned in that skeleton of Calc 1. Those basic things like limits, derivatives, and integrals are now done with more than one variable, hence the name multivariable calculus. So Calc 2 is kind of like, in some sense, an advanced version of Calc 1. You're taking everything in Calc 1 and you're building upon it and you're making it harder. There's applications of integration in Calc 2 that are super, super tough. The disk and shell method destroy people. When I took Calc 2, that was like the one thing that really destroyed me. I did not understand it. It wasn't until I had to teach it that I finally really understood it. And there's processes in Calc 2 that are just so much longer. The technique of trigonometric substitution. I remember looking back at the end, during the end of my course, looking back and thinking, wow, trig substitution was really, really crazy. So yes, Calc 2 is definitely the hardest in my opinion, barring strange circumstances like you have an insanely ruthless Calc 1 teacher or an insanely tough Calc 3 teacher. What do you think? Do you think Calc 2 is the hardest? Which one was the hardest for you? Leave a comment in the comment section below. I'm curious. People always talk about it, right? People call Calc 2 a weed out course, and I really don't think there's anything. I don't think there's such a thing as weed out courses. I really don't. Yeah, I don't think it's a real thing. Anyways, keep doing mathematics, and if you found any value in this content, feel free to hit subscribe. Take care.
Taking a quote from Stephen Strogatz, since Newton, mankind has come to realize that the laws of physics are always expressed in the language of differential equations. Of course, this language is spoken well beyond the boundaries of physics as well, and being able to speak it and read it adds a new color to how you view the world around you. In the next few videos, I want to give a sort of tour of this topic. The aim is to give a big picture view of what this piece of math is all about, while at the same time being happy to dig into the details of specific examples as they come along. I'll be assuming you know the basics of calculus, like what derivatives and integrals are, and in later videos we'll need some basic linear algebra, but not too much beyond that. Differential equations arise whenever it's easier to describe change than absolute amounts. It's easier to say why population sizes, for example, grow or shrink, than it is to describe why they have the We last left off studying the heat equation in the one-dimensional case of a rod. The question is how the temperature distribution along such a rod will tend to change over time. And this gave us a nice first example for a partial differential equation. It told us that the rate at which the temperature at a given point changes over time depends on the second derivative of that temperature at that point with respect to space. Where there's curvature in space, there's change in time. Here, we're going to look at how to solve that equation. And actually, it's a little misleading to refer to all of this as solving an equation. The PDE itself only describes one out of 3 constraints that our temperature function must satisfy if it's going to accurately describe heat flow. It must also satisfy certain boundary conditions, which is something we'll talk about momentarily, and a certain initial condition. That is, you don't get to choose how it looks at time t equals 0. That's part of the problem statement. These added constraints are really where all of the challenge actually lies. There is a vast ocean of functions solving the PDE, in the sense that when you take their partial derivatives, the thing is going to be equal. And a sizable subset of that ocean satisfies the right boundary conditions. When Joseph Fourier solved this problem in 1822, his key contribution was to gain control of this ocean, turning all of the right knobs and dials so as to be able to select from it the particular solution fitting a given initial condition. We can think of his solution as being broken down into 3 fundamental observations. Number 1, certain sine waves offer a really simple solution to this equation. Number 2, if you know multiple solutions, the sum of these functions is also a solution. And number 3, most surprisingly, any function can be expressed as a sum of sine waves. Well, a pedantic mathematician might point out that there are some pathological exceptions, certain weird functions where this isn't true, but basically any distribution that you would come across in practice, including discontinuous ones, can be written as a sum of sine waves, potentially infinitely many. And if you've ever heard of Fourier series, you've at least heard of this last idea. And if so, maybe you've wondered, why on earth would anyone care about breaking down a function as a sum of sine waves? Well, in many applications, sine waves are nicer to deal with than anything else, and differential equations offers us a really nice context where you can see how that plays out. For our heat equation, when you write a function as a sum of these waves, the relatively clean second derivatives makes it easy to solve the heat equation for each one of them. And, as you'll see, a sum of solutions to this equation gives us another solution, and so in turn that will give us a recipe for solving the heat equation for any complicated distribution as an initial state. Here, let's dig into that first step. Why exactly would sine waves play nicely with the heat equation? To avoid messy constants, let's start simple and say that the temperature function at time t equals 0 is simply sine of x, where x describes the point on the rod. Yes, the idea of a rod's temperature just happening to
Hi, this is DJ. I'm a machine learning engineer at True Theta, and in this video we're going to ask the question, why is reinforcement learning applied so rarely in industry? It's a good question, because reinforcement learning is really attractive, but except in truly rare cases, it's really not the right choice for industry applications. I mean, I understand why people love the topic. I'm one of them. The math is beautiful, and it tackles a problem statement so general, it can describe almost any goal-oriented task. And that's why I spent such a long time putting together my series on reinforcement learning. But since then, I've gone to work with companies on applied RL, like for marketing, e-commerce, and quantitative finance, and I find myself recommending and building with much more traditional techniques. I mean, I'm making this video almost out of guilt, and I feel like I have to share this practical reality. I'll start by giving more of the story. After my RL series, a handful of people reached out for help with applying RL. I was at Lyft at the time, so I wasn't available, but it was pretty exciting. For example, one reach out came from someone at the Department of Defense, which was quite interesting. The others were from small or mid-sized tech companies. So this had my attention. Also, as I mentioned in the series, Lyft had deployed into production a successful application of RL. So I was convinced this was the next wave of applied innovation. In fact, that was enough for me to take the leap and start an applied ML company to work on projects like this and others. My first step was to get a better understanding of tried and true best practices for real applications of RL. So I reached out to a bunch of people with applied RL experience. I ended up speaking with engineers and scientists from Expedia, Siemens Energy, Amazon, Pinterest, Microsoft, Meta, ThoughtWorks, and a handful of startups. What I discovered is that in most of these successful applications, a pretty generous definition of reinforcement learning was used. This wasn't totally surprising, since it's good marketing to say you do RL, and there's no clear boundary between RL and not RL. In fact, Ben Recht has a good article on this problem, describing how the most general definition of RL is learning how to map situations to actions, which includes virtually everything, and the least general is specifically connected to the techniques favored by the RL literature. This means the label reinforcement learning is found on a lot of applications, and those applications aren't necessarily what you expect. For example, in one serious logistical application of RL, the team used a huge, carefully designed simulation of what next week's shipping and transportation outcomes will be. They feed a bunch of parameters specifying how they'll operate next week, and the simulation spits back a huge collection of outcomes, which they can evaluate by looking at things like expected delays or costs. The goal is to pick the parameters that make the simulations look good. Now, is this RL? Well, since the parameters could be interpreted as a policy and the simulation is the environment, you could call it RL, or you could call it by its classical name, simulation optimization, and impress a lot fewer people. To me, this just feels like vanilla stochastic optimization because there's no critical notion of time, state, or sequence-dependent actions. I also learned if something is squarely RL and is commercially successful, they're often in really exceptional circumstances. For example, contextual bandits should count as reinforcement learning. It has the explicit concepts of time, states, action, and rewards, and uses the same theory and often notation as the RL literature, and it works commercially, like for dynamic pricing and recommender systems. That's actually why I wrote some explanations for how they work. However, contextual bandits are a seriously truncated flavor of RL. It requires that there's only one action and an immediately observed reward attributable to that action. After that, the episode is over. It's literally many single action simulations. Now, in textbook RL, the goal is to optimize a whole sequence of actions, often under noisy and sparse rewards, which is exponentially harder. By assuming the real-world application has the benefit of single-step actions with immediate rewards, contextual bandits sidesteps one of the most difficult challenges of RL. That challenge is the credit assignment problem, where actions need to be attributed to long-term consequences, which is normally totally ambiguous. So since they only apply to these especially simple real-world cases, bandit algorithms are far from the technologies dominating video games and AI demos. Okay, so we should ask, is there any full-fledged RL that is commercially successful? Well, I only found one convincing case, and that was from Siemens Energy. Now, for many years, they've made a strategic bet on RL for energy management, amongst other things. And as you'll see, their cases, again, really are exceptional. First of all, they're studying physical systems, where precise laws of physics can be applied. This allows their simulations to be much more honest reflections of the real world than what you'd see in other commercial applications, like those modeling human behavior. Second, they deal with huge data collected over very short timescales, where an adjustment needs to be made every few milliseconds, like balancing turbine flow or managing voltages across a grid. In this case, long sequences of actions need to be determined in quick succession and in an environment where you can't collect a fixed batch of data to know it.